Yes. Yes. Okay. Now I'll. Again, this is my voice just speaking out to the people in the auditorium. Excellent. So that anyone listening can get the sort of the room. I've turned the mic on. We are broadcasting it.
Yes, people will start. Well, who knows if they'll.
I used to be able to make a couple of animals. I used to be able to do this. I don't remember how to do it, but I used to do that.
Yeah,
shadow thing.
The shadow boxing.
Ah, bravo.
10 seconds.
Thank you. 4, 3. Yes, and what we don't have is Kevin. There goes Kevin. Kevin's running for the hills. Yeah, just go all right. How about that greeting? There being no ladies in the audience today, gentlemen, welcome. I had planned something perfectly ordinarily politically pertinent, but events intercede. So I'll just ask if you would care to be a passenger in a smart car on a winding mountain road that decided that to save the lives of a busload of passengers, that it would drive you off of a cliff. And you can apply that to whatever other worldly situations come, and ask if you have heard of a Belgian kiss, like a French kiss, only more Flemish. All right, we're raising the interest level to level 4th. Shelter in place, please. Those of you here, thank you for coming. Those of you then and wherever you're watching, my thanks to you all. Kevin?
Okay. All right. I want to know where Dr. Ting is because he's up. Oh, there he is. Okay. Right in front of me. Okay, it's one of those right in front of me and I still didn't see it. I wanted to mention that we're going to be passing around the lunch menu and the checkoff sheet. So order your lunch. If you're going to be sitting there with it in front of you rather than checking something off and passing it on, just pass it on. It'll be in the back after everybody else is gone. And if you're paying close attention to the speaker and you can't spare any for the lunch, just pass it on. Just don't hold it up. Our first speaker, welcome to those of you on the interwebs, and welcome to you in posterity, where this is going to be stored, I guess, in the cloud somewhere. And welcome to those of you who came in corpus today. The first speaker, Dr. Ting. So when you get up here, introduce yourself and get into your talk. I'm not going to be moseying up for that purpose every time. And once again, welcome to 4th Day.
Let me see how.
I think we have prepared a fourth programming challenge for you, and it's I don't have any shot. It's this is Arduino kit, and I have 3 sets set up in the back on the back table. So if any of you are interested in participate, go grab one computer, and then you can play with it. I think this this programming challenge is actually quite simple. It is an 8x8 LED array that's placed on Arduino shield, and it's all being wired up, so you can just sit down and type something, and it would lit up any number of the LEDs. So the general description of the setup is here, and the software driver is already in place. If you use the E4 that's already being installed in the on the Arduino. Let me see. I also give you a sample code which shows you how to lit up any of these number of LEDs. So I think there's already one entry there. That's very interesting. If you can see it. Why it stopped? Okay, yeah, it's running. So see what you can do with it. Any question? Any participants? Okay.
What's the grand prize?
Oh, well, I don't know. Yeah, I thought I'll bring a bottle of wine, but I forgot. Okay, thank you very much.
I'll keep you on schedule by talking really fast. I'm Leon Wagner from 4th Inc., and I'm going to talk to you about a project that we worked on this year. So instead of talking about products and 4th development systems, I'll show you something we actually did with this stuff. This work?
It was. Okay. It is done.
It's doing it. There we go. It made a little happy sound here. All right. This is about the Radius 8200 series antenna controller, which is a project that we've been working on since January. A company called Radius Labs came to us and asked us if we would help them do the programming and design on a new antenna controller to control large Earth station antennas tracking geosynchronous satellites. Well, we already know how to do that, so that was nice. And it turns out that the people who constitute this group had worked for another company, and we'll get to that in the history section, that had done a similar project about 20 years ago that we also participated in, although at a much lower level. So in January, and they also happen to be geographically desirable. They're in the San Diego area. So as for me living in LA, it was a nice, easy drive, as opposed to getting on an airplane and going halfway around the world, which most of our projects are. So very nice. I went to San Diego. This is a representative, this is actually a picture I took with my iPhone of one of the antennas that we are controlling, just to give you an idea. So this is an 11-meter antenna pointed sort of south along the horizon. It's located up in Brewster, Washington, on a plateau in the foot of the Cascade Mountains. It's a beautiful area and really hard to get to.
Here's the ancient history part. We worked on a system called the Model 7200 for a company called Vertex RSI. You can see their logo up in the left side of the screen. And at the time, this was a very, very advanced, sophisticated controller. It was doing things that nobody else had done before. It had a very large display. It's an electroluminescent display with not much in the way of capabilities. It was characters only. It had reverse and forward video attributes, and you could set your font to one of two sizes, small and big. And that was the extent of what it could do. It had a keypad, and it had a great big button with a switch, with a lid over it that let you disable all of the drive power to your antenna in case you had a panic in the control room. You could, by God, shut it down. This was developed in the early 90s. I think I came aboard that project in 91 or 92. It took them about 3 years total to develop the whole system. It was a 68030 running at, I don't know, 60 megahertz or something. Randy, did you work on this? Yes. Did you work on this?
No, I helped teach it.
Oh, okay. A lot of people had their hands in this project. I did a lot of the low-level stuff. I did the implementation of R4 onto their 68030 board, a series of boards. They originally used one that they bought, and then they developed their own. We did all the implementations for them. I did all the low-level drivers. I think I made the display talk interface to the keypad, going out the backside, all the relays and optical inputs and so on. But that was the extent of my involvement. So to say at that point I knew how to track satellites, absolutely not. I knew how to give you the stuff that would help you track satellites. So moving on from there, in January I went down to meet with the guys at Radius. We all got together, Ron Oliver being one of them. And this is what we had. We had a drawing on the whiteboard of sort of a high-level system view of what we wanted to do. We had a few details about what the various components would contain or be made up of. And we set off to actually begin the hardware part of the design. We selected some hardware components. The first round of selection we threw out because they were inadequate. We ended up contracting with someone to build some boards for us to do the I/O that we needed to do the inputs and outputs to control the antenna. By April of 2015, which end? This end? Can I point with this? We had a demo up here on the left. We had just a small dish antenna. We had it motorized in 2 axes. We had our controller built and the beginning of our user interface to display. This was at the National Association of Broadcasters convention in Las Vegas. And that's the place where people go to buy Earth Station stuff, apparently. That's, in case you don't recognize them, that's Ron on the left. So this was the team from Radius and one of our guys showing this off, just trying to attract some interest. Could it track satellites at this point? No, but it was really close. It could do all the control stuff to point very accurately at where we wanted to point. It did not yet have the feedback loop working to actually figure out what it was pointing at. That was next. So this is in April. So we started in January. By April, we had a working prototype of all the hardware doing positioner loops. A little discussion about the axes you're controlling. There are two principal axes you control when you're tracking a satellite and an optional third one. And this is not a great drawing. Azimuth doesn't quite show you. Azimuth is this way. Elevation is this way, and polarization is this. And polarization is only interesting if you have a linear polarization and you have to orient the center of the antenna to align with it so you're receiving the signal. If you're across it, in that case, you'll null it out. So for our inputs, we have position transducers on azimuth and elevation. And those are either resolvers, which are electromagnetic devices that as they turn, they are stimulated with a high frequency, and we pick up the sine and cosine on the other coils and figure out where we are. Not very precise. We only get 1/100th of a degree accuracy with that. We prefer these days to use optical encoders. They're really nice. They're smaller, they live longer, they're not subject to all the failures of the electromagnetic devices, and they give us much better precision. We can measure to at least 1,000th of a degree, which is very nice when you're tracking things that far away. For polarization, you kind of need to know where you are, but not all that accurately. So if you're within 1/10 of a degree, good enough. So we put on a resolver or a cheap optical encoder on the polarization. And again, that axis is optional depending upon whether you're tracking things that have linear polarization. We have some limit switches at one end of each axis. You want to know if you accidentally left the motor on too long and came to the end, it has to A, absolutely cut the motor off, so that's done outside our control, and B, give us a signal to let us know that we've done that so we can sound an alarm and stop tracking. And we have that at both ends of each axis. We also have a beacon receiver. This is the feedback loop, so that whatever we're pointing at, we can set the frequency to its beacon. Every satellite sends out 1, sometimes 2, sometimes 4, depending on the bands, beacons, which is just a continuous wave. And so all we do is use that to center on and also to peak up on. By June of 2015, we had the feedback portion of the loop working and all of the tracking algorithms implemented. So April, May, June, 2 months. I was really busy. I did all this. And we had our first candidate test site. This was an antenna that was part of a project that was part of this very large antenna farm at a teleport in Brewster, Washington, that had been largely abandoned. It was built in 2004 and not quite commissioned. It was just about to go into service. Has anyone heard of Astrolink? Astrolink? Vaguely. It was a project. It was many participants. Lockheed Martin was one of them. It was a project that went defunct just at the time the antenna was built. So it stood there idle for 11 years. And a lot of its instrumentation had been removed, but it had enough stuff there to still work for us. It had position transducers. It had some very old size 11 resolvers on it. And it had motors that hadn't been run in 11 years. And so on. But they gave us free rein to use this antenna. All we had to do was get there. So we flew up there, brought all our stuff along, got the thing instrumented, got everything hooked up. And can you see me sitting there? So that was my office that week. It was 109 degrees in the shade. And you can see the shade. All I had to do was keep moving my table and follow the shade around for those 2 days. Pardon? I have to say that after it stood idle for 11 years, the first time we fired up the motors at full speed and ran them through their full travel, it made an unbelievable sound. Very loud groaning and complaining. Here are just some close-up pictures of the position transducers. So if you saw let's go back just to there a second. The pivot point for the azimuth is right here. The pivot point for the elevation is right here. And you can't see it, but the polarization is on a panel right here. We have the cover off, so the back of the hub is open, so we could get in there to play with it. This was really fun stuff. So there's a close-up picture of the resolver that was giving us our position feedback for azimuth. This is a close-up of the resolver that was giving us our position feedback for elevation. Here's the limit switch that we have in azimuth, and it's a single switch with a post, and the post goes one way or the other, and it bumps that switch. So it either presses it one way, or the other post comes around from the back side and presses it the other way, so you can tell which way it's doing it. For outputs to control this thing, we control the motors. This is called a bang-bang controller. All we can do is turn the motors on and off and change their speed. It's not a proportional speed controller because we're moving so slowly. If we were tracking a low Earth orbit or medium Earth orbit satellite that was moving very quickly, we would need proportional control because you have to basically do this. But for something that's geosynchronous that almost doesn't move at all, you can get by a lot cheaper with just a motor controller that lets you control the speed and the two speeds, fast and slow, and the direction, forward and reverse. So for azimuth and elevation, we have basically the same sets of controls. For polarization, since it's not used very much, all you have to do is move one way or the other. We don't care about the speed. We're not in a hurry to get there because you're not going very far. In the case of azimuth, where you might be swinging all the way across to go to the other end of the horizon, you want to be able to speed it up a little bit and then slow it down so you can get the precise positioning at the end and not just overshoot the end. And we also have an output for an alarm, just in case something goes wrong. You want to be able to tell somebody about it. So we provide a contact output that can be used for an audible or visual alarm, or not at all. Here's a close-up picture of the motor controllers that are in the cabinet. So all of the programming of the motor speed and so on is done through the keypads on here. Our interface to these are direction, on, off, and speed. And we get one feedback from them, and that's a fault. If you try to do something bad, or if the motor becomes jammed and gives an overload, we get a fault condition back from it, and we can sound an alarm. And of course, that never happens. There are 3 computers in use in this system, usually 2, optionally 3. We have a transducer interface that hooks us up to the encoders. So the optical encoders use a synchronous serial interface of various flavors and protocols depending upon who made them. We compressed all that down into a single board that looks like this. So no matter what transducer we hook up to it, it figures out what it is, and it provides a consistent stream of positions out the other end to go to our position controller. There's a second board that looks similar to this that's used for resolvers, but it has all the stuff on to do the interface to those electromagnetic things. So we have to control the gain and the frequency and various things. And the controller, I/O controller board, does all the positioning. So you tell it go here, and it does based on the feedback. And it does all the fault detection. Both of these are using a Cortex M4. It's actually a Freescale Kinetis K64F, if you like that sort of thing. And it's running our SwiftX cross-compiler for the ARM. The user interface is a touch panel PC. It has a 10.2-inch panel PC with Windows 7 embedded. There's a long story behind that for everyone who's a Windows hater. I'm not a Windows lover, but it sure was fast to develop on this thing. And time was of the essence. I mean, you saw our timeline from whiteboard in January to working prototype in April to functional control in June. We really had to move. And that's done in our SwiftPorth product and made extensive use of our Swoop object-oriented package. Every element of every single thing in here, including the calculations for the orbital mechanics, are all objects. I know. It's true that when you give a kid a hammer, everything looks like a nail. This was my first big OOP thing using Swoop. It was a delight to program in. That's what the user interface looks like. This is the front panel of the chassis. This is an earlier revision. It's been refined a little and looks a little less prototypey now, but the touch screen is pretty much what it looks like. It's a very nice, clean user interface and very intuitively easy to use. Anybody who works in an Earth station who knows what you need to do can walk up to this thing and start tapping buttons and get it to do something useful without a user manual. That was one of our design goals. Well, we had an expert in user experience. Marlon Overson did the entire design for the user experience. And it's, yeah, down to the placement of every pixel and every color on here. This was all done by him. And it's absolutely beautiful. And everyone that we had come in to view this while we were setting it up was oohing and aahing about it. So we knew that we had gotten it right. I'll actually show you a live one running in a few minutes. This is a close-up of the touch panel PC with the beautiful Windows 7 Ultimate screen on it. This is the rear panel inside the chassis. And if you look along the bottom, lots of nice I/O connectors. COM ports, because some of the things we talk to have serial ports. Some of the old tracking receivers give us a serial interface. So we have COM ports, a bunch of USBs. What?
Those were the days.
Those are still the days.
For this type
If you go into an Earth station and they've spent hundreds of thousands of dollars on tracking receivers and they have serial interfaces, guess what? You provide a serial interface. It's that simple. Modern things, USB and a couple of Ethernet ports on here as well. Our internal network for all the communication with all of our boards is Ethernet. So one of those ports is our private network for Ethernet. We're just running UDP, no TCP/IP. So TCP/IP for one thing, one of the receivers is TCP/IP, but everything else internally is UDP, very fast. So all of our control and status packets going back and forth are UDP frames. In our original drawing back on the whiteboard, if you looked really, really closely, you would see a link between two boxes and it said SPI because we were originally just going to run some SPI around inside the chassis. And we realized that if we did it using Ethernet, since we already had the ports on our CPU boards, I'll pull this off. So all these boards have this exact same footprint on, and they all use the same CPU board, just to make it easy. The CPU board that we chose already had an Ethernet port, and we realized this gave us a lot of flexibility. We could put these anywhere we wanted. They didn't. We were locked into the mindset of the old system that everything had to be in the chassis, and suddenly we realized we could take the controller and instead of running 100 wires out through a big fat snake cable to the box close to the antenna where all the relays and controls and motor controllers were, all we needed to do was run an Ethernet out. And then a further realization was made that if the switch that we put inside the chassis that connected all the boards together had a fiber port, we could run fiber out to the station, and then we were lightning proof. So a lot of great things happened out of just deciding to go with Ethernet for this. So the touch panel computer has two Ethernet ports. One of them is provisioned just to do our local network, and the other is provisioned to go behind a firewall to the public network to provide remote MNC access to it through several layers of security. And I'm actually going to use that second port to show you a live user interface on that antenna in Brewster. This is just a close-up picture of our screen while the antenna is in standby. And just a few of the visual elements. We're always showing what we know to be the current position based on our transducers. If we have a receiver hooked up, we would see its level here. It's right now, it's not pointed at anything, it's showing nothing, but we'll see something live. It shows the mode. There's a place down here in the bottom to show you interesting status messages. So when this is blank, it's very, very calm and quiet. You can look at this from across the room and know that nothing is going on. And then the user interface consists of the buttons along the bottom. Great big fat buttons with enough room between them that you don't accidentally roll from one to the next. To the pixel. This is a sample of how you select a target. You think of your satellites as targets, so you want to point at something. Here's your target. This is a list of ones that we knew about. Oh, those are real. The very first one we ever tracked was SES-2. And right now, we are, in fact, tracking AMC-2, which is a very old satellite. And when satellites become older, they expend less fuel to hold them in position. They hold them in position this way, but not so much up and down. So they drift into an inclined orbit. And then they get a lot more fun to track, because you don't just point at one place like you would with your home dish antenna to something that's being kept in position. You have to be able to follow it as it makes a figure-8 pattern up and down on the horizon. That's the fun part. When we're first acquiring a target, that's where we figure out if it's inclined. We calculate all the places it could possibly be on that figure-8, and we just iterate through them. So we go from that, calculate the look angles, the place we want to point the antenna, and we trace that figure-8. And we do that as quickly as we can until we see the start of a signal. We wait till the signal peaks up, we stop there, and then we actually position in on the satellite and lock in. That only takes a few minutes to do that. It's not too bad, and it's really fun to watch it when it's doing it, or to listen to the motors while it's doing it. Here's a picture of a satellite that's in inclined orbit, like AMC-2 that I was just referring to. So you can see what it's doing as it's moving around. This is a sample of the log data that I was acquiring while doing the testing on AMC2. What are we looking at here? Azimuth. So I just captured the continuous log every second, taking samples of where we were pointing target azimuth from the calculations from the algorithm. And you can see that it's very, very smooth following the satellite. No jumps. When we first hooked up to this antenna that had been sitting idle for 11 years, we were seeing this thing jumping all over the place. And we determined that we had a problem with our position transducers, those very old resolvers. And so we took the can off to look inside to see what was going on, and water came out. No, they have since been replaced with optical encoders. Long story. And this is the result of the replacement with the optical encoders. I should have saved a picture of that first one because it just had jumps all over the place. Very obvious that something was going wrong. So that's the end of the picture show. I'll show you. This is live from Brewster. So we're actually tracking the target. I can carefully step through a couple of the things on here without disturbing it because I don't want the test to stop. If I were to click standby, it would literally go into standby and stop everything it's doing. In target selection, I can go and choose a target to track. I can edit its parameters. I can delete one I don't care about anymore. I can set up a new one. Very obvious what these do, right? If I want to manually adjust where the position is, I can click on manual and it will bring up some stuff that will allow me to turn the motors on in manual mode. These also correspond to the physical buttons on the front panel, but when I'm at home in LA, I can't reach that far to push the buttons. So I gave myself some, these are just for me, some radio buttons on here to do that positioning. And in the setup part, this is really interesting. These are the things where you set up the things about the antenna itself, about the transducers. So here's our name of our antenna, our polarization type. I have it set to circular. I turned off the polarization. We're doing an experiment right now. So I just put the pole there, left it, and turned it off because I'm not interested in moving it. So you can see that that third column at the top is absent. We set up everything we know about our encoders, so we have to give each an offset because who knows where they were when they were first in, so we have to be able to tune the antenna to the actual position. We give it some travel limits, so we say don't go past here. We tell it what it's like, what the characteristics of the motors and the transducers are to detect automatically if we have any faults. Is it going the wrong direction? Is it moving when we don't expect it to? That's called a runaway. Is it not moving when we want it to? That's called immobile. And all of those things we do by measuring over a period of time, limits in degrees. So you can see here, if after 14.628 seconds, it has not moved at least 0.02 degrees, it's immobile. If it has, in that same period of time, we were expecting it to be sitting still, and it moves more than 0.04 degrees, you have to allow a little jitter because the wind may blow. You might have an earthquake. I mean, different things can happen that could, or just a little noise on the line. So, but if we say, well, if it's moved more than 0.04 degrees, it's run away. These values were determined by, where is it? Where's the button for that? If you see the button down here in the lower right-hand corner, Setup Wizard, on an initial installation or after changing out parts, I made this very cool thing called the Setup Wizard, and it's really fun to watch it in action. It moves everything through the full motion in both directions, up and down, polarization, until it hits the limit switches, figures out where they are, backs off a little bit and says, okay, that's about as far as I ever really want to go. Then it goes back to the center and it starts making little iterative moves here and there, farther and farther and farther, and it figures out all of the characteristics to use to give you initial values for all of these things. It figures out if you're moving at the fast speed, how close do I have to get before switching to the slow speed to do the final part of the tracking. So you want to maximize your fast speed and come in as close as you can before you switch to the slow speed. So it figures all those things out and then populates all of these fields And then you can go in and manually edit them if you want to tweak them a little bit. So that was a really great thing. And in the old days, you would have to find somebody who was really smart and knew how to fill these in, or do like everybody else did and just guess.
Well, that's interesting. With all that data, you can actually tell if motors fail over time too.
Yes. And serendipitously, while we were there working on this, we had a stuck relay out in the drive cabinet. One of the relays that we were telling to turn off didn't. And that motor kept running, and it ran all the way to the end, hit the limit switch, and kept going. And we were able to detect that, and we were able to shut all the power down because we have one master output called drive enable. So when all else fails, you take drive enable away, and you hear the contactor out in the cabinet go boom, and everything stops. And we were able to save the motor from burning out or from grinding the end off the jack screw. So that was kind of interesting. So the other thing I'll show you, since we're all fourth geeks, is what it looks like to do a little development on one of these. So this is one of the projects for one of the boards. It's done in our SwiftX systems. And to talk to the board, sorry, I just got this computer and I don't know where the ports are. Let's try this, or if it'll even work. So this uses a USB. Am I out of time?
No.
Okay.
Doorbell.
Oh, it's the doorbell. I haven't been watching the counter. This has an open SDA port for development over USB. So it's giving us the Cortex-M JTAG through a little translator chip over USB. So I plug it in. At least it's alive. And then I just load up all my code, establish a connection with it. And there it is. It's up and running. That's it. Well, that was nice. So that was the whole thing. Were you waiting for something? That was loading all the code for this very large application to do all the positioner loops and all of the setup wizard and everything. And then loading it into memory and starting it up. And at the end, when it said, OK, it's ready for me from the keyboard to do things to it. But it's also running the application in the background because it starts up automatically. So that's it. Yeah. I mean, this is typical of using this environment to do development on most modern chips, especially if it has flash in it, we could just flash it over the interface. We do that directly. It happened so fast you didn't see it. A little window popped up when it was flashing and went away. There's a window in a progress bar and it goes flash, and it's gone. Okay. Any questions?
How much of this can you do sitting at home? You have a webcam.
Oh, I can do just about all of it. We tried to put a webcam on it. We had one with us the last time we were there. And one of the techs was with us. And he found that from where you remember in the picture at the beginning, the little shelter?
I do.
Otherwise, I can go back to it. We tried, all we could do to get to our network hub, which was in the shelter, was run out the side where, if you see that cable trough coming out of the side right there, we tried putting the camera right up there because we could go in through the cable trough because we couldn't leave the door open, obviously. And we were so close to it and we didn't have a camera with a short enough lens that all we really saw was just sort of like the back of this. So it would have been nice if we were able to find a place farther away. No. We do have an Ethernet, but it's a physical connection. No, there's no Wi-Fi. They gave us a little tiny Wi-Fi hub inside the shelter just for when we were there, but that would not ever stay present at a relay station. There's a nearby shelter just behind us, so we may ask if we can mount on that next time.
Flash all of its pieces from
Yes, yes, I can, and I do.
Take every piece of this.
Yes.
Is there a
I
power switch, internet power switch, so that you can reboot the whole thing? Should that become necessary?
No, there isn't.
Does the controller read in 2-line ephemeris data?
Say again?
Does the controller read in 2-line ephemeris data?
No, it doesn't.
How do you specify the orbital parameters of the satellite?
You give it the box center and the inclination.
And it tracks once it locks
It's
on?
close enough. Yeah, we took the 2-line ephemera sets and just took out some of the farther away variable things, just zeroed them out, and it turned out that what that drew versus what we drew just by figuring out the basic figure eight of the orbit was close enough for us to find the edge of it.
You like ignore the second derivative part?
Yeah, because it contributes so little to it that it doesn't really matter. It might, when you come out near the edges, it might flatten the 8 a little bit, or it might make it a little bit wider, but you're still close enough that you see enough of the signal that you can then lock in on it once you're there. So that was a great revelation. The other thing we do is we store history continuously as we're tracking. And then based on the history, once you have enough history, then you don't have to be running all the calculations. You can just do everything based on the history. So you can do a little bit of prediction. And when you're doing the prediction, you're moving the motors much less often. And so if you were constantly step tracking in on this thing, that's the algorithm, step track. If you were doing step track all the time, you would just grind that screw down to nothing right where you were. And doing this, we hardly move it at all, or move it as little as possible. On an inclined orbit, yes, of course you're moving, but not as often.
I noticed you're using TeamViewer to get the video.
Yeah. Mm-hmm.
Is the Swift port going through UDP or through TeamViewer?
Not sure what you mean.
It's the Swift port interface. Is that going over internet, or
No.
do you use the TeamViewer?
SwiftWorth is running on the box, providing this full screen graphical user
So you have a
interface.
local Swift port.
Yeah, there's a TeamViewer server
Server.
on that box. And the client, yes, correct.
Oh, so you're doing remote Swift port. You're remoting into your Swift port
Yes.
through TeamViewer.
Yes, SwiftWorth is running on the touch panel computer that's sitting in that little shelter.
Yes, correct.
And what?
I use TeamViewer too.
Yeah. So when I do a remote update, which I do quite frequently when I'm doing development, all I do is I stop this application from running. It comes back to the Windows desktop. I take the Windows installer for the new update, drag it from my desktop to its desktop. It copies it over, and then the new installer appears in the desktop. I run the installer. When the installer is done, everything is in place, and then I start it up. And as soon as it starts up, the SwiftWorth application goes around to all of its remotes on the UDP, and it says, "Are you there? What version do you have? Oh, you need an update. Here it is." And then it just pushes all the updates over. They reflash themselves, and then they all come up, and then we're happy.
But that's all locally on site.
Yes, and all of that is built into the binary that the SwiftWorth is running. So the binary, the exe file of this program contains all of the binary images of all of its slaves.
But you're using TeamViewer as your security layer.
No, I'm just using TeamViewer for convenience to give me remote access to it. Yeah, but it's firewalled.
It's firewall
Yeah.
itself, but that
And VPN.
the TeamViewer allows you security on who can access it.
Oh, yes.
Yes.
And it's only through their VPN as well. Right. Yeah. Yeah, not just anyone can hop in. If you knew the TeamViewer ID and get to it, you can't. You have to go all the way around and in and then in. Yeah.
Well, I fear it's time to use the hook.
Okay, sorry.
One last quick question. What UI tool for this involved here?
SwiftWorth. Using Swoop, our OOP package. Every single element on there is an object.
So, what do you use for a object-oriented paradigm?
What do you mean?
Oh, okay. When you do object-oriented programming, you have to do object analysis, design, and implementation. Lots of individual implementation support, but I assume you model the system in an object-oriented fashion.
Yes, and I suggest you read the Swoop chapter of the SwiftWorth reference manual, which is available on our website with the eval version, and it goes into that. I'm sorry. Thanks.
Have the delivery from Treehouse here at the proper time. So we want to know what you're going to eat. So they have burgers, they have pizza.
Pizza is the preferred meal for 4th Day. Makes things a lot simpler.
So there's a sign-up sheet here. You just check what kind of pizza slice you want, or if you need something special, write down your name and the menu item. And behind the first sheet is a menu with all the prices and description and everything. So keep track of how much your lunch costs, and you can pay at the table over there.
What time would that be?
The final lunch fee will probably be after the food arrives.
Oh, thanks.
We'll shoot for noon, but it's kind of non-deterministic.
Shoot the moon. You can shoot the moon, not the moon.
We have beer, so don't worry about beer. No beer, no drinks.
Yeah, beer seemed counterproductive. You want to be in charge of the beer next time? You're welcome to volunteer for beer. I'll participate. Consumption goal.
Well, can you hear me? Well, yeah, I don't know. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Hi, my name is Alexey Shpezhenko, and I'm here not the first time, but I can recognize many of you. And today's my talk is about JavaScript and a force, and going back and forth with JavaScript and force. So I will start with a little quiz, and don't treat me dumb, but how many of you written force code? Like, good. Okay. So how many of you written the force compiler in your life? Okay. So it's actually more than more than that. But I'm pretty sure it's because when you write something in force, you actually write in the compiler itself. So you're extending it, right? So another question is, how many of you written a JavaScript code? Okay. So it's about the same. I would expect more because JavaScript popular these days, but how many of you written a JavaScript compiler or part of it? Okay, we have one. Good. So it's less popular to write JavaScript compiler than write if you're user of JavaScript, but it's still the case. It's new, and I know several compilers written recently and translators. So my experiment, I will present some experiments that I did recently. They might seem disconnected, but JavaScript and force will be the main topic on those experiments. So first, I will start with the statement, force is everywhere. And I guess that was the case when force started. Every small, well, you know, or little microcontroller, bigger system automatically get a force on it running. Because it was so easy to port it, and it was so much fun of porting it. So, and force is everywhere, but this everywhere is changing over the time. So there was small processors, and there was Unix, there was Windows, and force kind of followed all this trend over the years. But everywhere itself changes rapidly, and JavaScript is everywhere now. So I would say even more, JavaScript is everywhere. Means you running notebooks, and most probably each of your notebooks has a JavaScript in it. So, and the basic question is, can we actually translate force to JavaScript to force? And it seems dumb because I've seen so many projects trying to run force-like language in a JavaScript that it's probably obvious that yes, it can. But what can be done, and what is my part in it? So JavaScript, as new everywhere, is getting wider and wider. Yeah, you experience with JavaScript on your browser, and you can embed it in your web page. You can run jQuery on your web page, and you basically run in JavaScript. So it's now on the server and getting more and more popularity on the server. And I'm pretty sure some of you have written some server-side JavaScript code already. It calls Node.js based on V8 Google machine runtime, and has many interesting features to move industry on using it. JavaScript is on mobile phones, tablets, and inside your apps. And you may not realize, but many of your apps actually running JavaScript inside. It's just not very obvious that it is in. And JavaScript moving into embedded world. When I say embedded, you know, new generation calling it IoT, but it's still embedded. So there are several development boards which runs JavaScript on a board. Like Tessel is a company in Auckland, I guess, selling small little board which runs JavaScript on it. Esproina is even smaller. It's like USB dongle. And runtimes, there are more and more JavaScript runtimes for embedded world. And they're getting less and less requirements on the memory and CPU footprint. And there is one from there is one from Samsung, which is IoT.js. There is V7 from some Irish company. And there is Kinema.js is from Marvel, I guess. And actually, every of your set-top boxes, like TV sets, Roku boxes, may run JavaScript on it. You don't realize it, but it may do that. So there are some JavaScript facts. Again, it's may be repetition of Wikipedia, but I want to emphasize some of the things that may sound familiar to you. And first of all, JavaScript is dynamic. So what does it mean dynamic? It's a lot of things done in runtime rather than in compile time. It sounds familiar to force because force is a runtime. You experience force program being compiled and other force program and so on. It's untyped. Everything is a var. It's a little bit different from force untyped because untyped in the force means you put something in the stack, it's set it to bit, but you don't know is it signed, unsigned, you know, something, and you operate with it without knowing actual type of it. But in JavaScript, it means a little bit different thing. So if you have var, you declare it var, it may be floating point, string, number, integer, or reference to something. You have to discover it. It's also interpreted. No explicit compile stage. And there is no binary or bytecode. So everything comes as a source code and get interpreted, and that code can interpret another JavaScript code and create a JavaScript. So in that sense, it's very similar to what Force is doing, because you can extend your compiler by writing some code in runtime. No compilation required. It is multi-paradigm, so it's imperative, object-oriented, and functional. There is a lot of features coming from Unix world. One of those is, streams. If you know that how standard input, standard output, and standard error works in Unix world, you know what stream is, right? So it's you can continuously stream some data through application, and it's not necessary. So this is just two examples of standard of streams you can experience in Unix system. And Force, like specifically Node.js, has concept of streams and heavily rely on that concept internally. And also, interesting fact that it was originally developed in 10 days in May of '95, which was year after last Sirius Force standard was released. So by the time that when we say Force stable enough not to release a standard for 20 years, JavaScript was just starting. So, but looking at the past, 95 was what, 20 years ago? It seems like old language already, right? So this is just some brief facts. So interestingly enough, because JavaScript is C-like language, even though internally it's more like schema or Lisp rather than C, but its syntaxes is C-like. It can be represented in a form of abstract syntax tree. And there is a bunch of projects which allow you to take JavaScript and represent it as a data structure. One of those projects is Mozilla. What do I have? So anyway, I will show you in the demo time. But there is Mozilla and ShiftAST standards which allow you to represent JavaScript as a program, as a data structure. And then you can store that as a data in JSON format, or you can load it, or you do manipulation with it as a data. So that's allow you to construct programs on the fly using just ways you deal with data and compile them, and then decompile them, construct again, and compile them, which is very important when you're dealing with Force or trying to implement Force interpreter. You want to do that. Okay, so I'm using this ST format in all my following experiments, so bear with me. I will explain how I use it. One other thing interesting is about JavaScript is arithmetic. Arithmetic is pretty interesting because as a normal number in JavaScript is float 64. If you type some a = 5, it will be float 64. Even this looks like integer. So to deal with some other types of numbers like integer, unsigned, float 32, and some other stuff, you have to do the tricks. But it's not like non-standard tricks. They're in the standard. They're hidden somewhere down below if you read it carefully. So for example, if you take x and do OR with 0, it means it's integer. X was integer, right? So it's sort of counting. And the only integer format JavaScript support is 32-bit integer. So x or 0 will give you 32-bit integer signed. If you want to get unsigned, you shift arithmetically down, right, by 0 bits. You explicitly casting it to unsigned 32 integer. And if you put plus x, means it is number. So it cannot be string or something else, right? It has to be number. Or if you do a floating point 32, you do some other stuff. So it also has typed arrays, which means you can create a region in the memory which has bytes in it, or words, 32-bit words in it, or 64-bit words, or something in the memory. So it will allocate a region of a memory without this dynamic and garbage collector running. It's just a region on a heap. It can be garbage collected though, but if you're not careful. But you have ability to allocate regions. And there are a couple of standards, AwesomeJS and WebAssembly, which is a way to deal with these low-level features of JavaScript, which usually you don't deal on your web page, but if you want performance, you can. So I will show you a couple of experiments I did. Experiment is actually force interpreter in JavaScript. I'm not asking how many of you wrote a force interpreter in JavaScript, but I've seen several of them. And my goal was pretty simple. I want standard force. I want ANSI standard force, not just some force-like interpreter, but the standard one. And I also want to use JavaScript as assembler. Remember, in ANSI force, there is concept of assembler. So you can create word which describes an assembly of your machine. So I want to use JavaScript as assembler of this machine. And I also want that my force be in a stream, not just, it's asynchronous stream. So you can feed it with data, like input stream, and it produces output stream. So it's completely asynchronous. If there is no data, it's not consume any CPU time. It's completely asynchronous to the external world. So you can run as many of them as you want in the same event loop. You don't need separate threads. You can run many of them in parallel. Not parallel, but asynchronously. And yeah, the obvious reason is to be able to embed force in a web page, in a server, in some environment where JavaScript is already running, but you want force there. And okay, and I will show compliance numbers, but let me show how it works in the demo. I'm not sure. Okay, yeah. Duck is a little bit dark, right? Okay, so basically, it's a web page which has two editor panes. One is the force. So black will be the force and white will be the JavaScript. So it's nothing specific about multiplying two numbers in the force, except you can do all other things in runtime. So you can say foo. Oh, that was 7. So you can declare something and call it, right? The interesting thing is that if you call something that is not on stack. So what is happening underneath every time I type something in a browser is it's set up timeout for 750 milliseconds or so. And if I stop typing, it's try to run this program basically on the right side. So what you experience that every time you stop typing, about like 50 or 200 milliseconds later, you get new system build, new force interpreter build from scratch. So taking your program, take it in the stream, passing by and printing something on the right. So if you do something more sophisticated than what I did, so you don't want to run something that is not completed yet. But if you do something, oh, sorry, and something like that, right? So you can have process of normal editor here is, I know the force is not picky about indentation. It's not Python, but so you basically typing and you executing it on the right way. So now you want to see how this word is built, right? So you want to actually do see foo, right? So you can see any word that is defined in this system, no matter how it was defined, with a force, with assembler, whatever. And what you will see JavaScript, because that's assembler of that machine. So every time you see this data stack push 10, it means something pushed to the data stack, right? Then you push in 0, and you do preparation for the do loop, right? There is a loop. So you'll see how it's organized underneath in a JavaScript world. So one thing is, so this is you define the word in the force, and you see how it looks like in the JavaScript. Right. So it's currently implementing all the yeah, it's currently implementing all the force core part, and it's almost passing the compliance test. Yeah, unfortunately, it's one long line. Yeah, I have to break it somehow, but it's pretty complete vocabulary. So what else you can do is you can define another word, but assembly word. So you want to define assembly word to have some capabilities that you don't have in the force right now, like drawing pictures or doing some weird I/O, right? So you can create some still force, but now it's getting JavaScriptish, right? And that's now force back, right? So so we get force, JavaScript, and back to force, right? So how this word will look like? Actually, exactly the same like you do in the first place. They will all look the same because all of them compiled into JavaScript. Yes, but now you can put anything in here. This you can do var t equal 5, right? So something that is just JavaScript. It's not a force anymore. It's not dealing with a stack, or it's dealing with a stack, but internally it can go wild as a JavaScript. So it's kind of one way of doing it. So now, while we're talking, how about just running instead of this? Oh, yeah. So the weird thing about force, one of the weird things about forces is that has very interesting control structures. So you can have a begin, repeat, begin, while, repeat, else, then control structure. And there is no, I don't know any other language that can do that. So how do you do that in a JavaScript? How do you translate it to it? Even though you don't have branches. So force, when it explains force standard, when it explains how force works translated into machine code, explain it in terms of resolving branch, points, right? Origins or destinations. And there is no branch points. There is no branches in JavaScript. You have to deal with something that is. So what you can do. Oops, where is my mouse? I lost my. Okay, just slow. So what you can do instead of breakpoints, you can do something like begin to while 3, while 4, 5, else 6, then 7, right? So you can construct any JavaScript flow control sequence, which is valid in JavaScript, using just few JavaScript concepts, construct. One of those is break. So yeah, you can construct and name those blocks. So when you construct a block, you name it, and it has label. Just block, do nothing except you can break from it. If is not very straightforward if, because it's doing the opposite of if. It's creating a block and doing if 0, break from it. So it's allow you to put else whenever you want after it. So you kind of get an if else construct, you know, it's the same time. And again, so all these breaks from L3, for example, break from L3 means you break to here, right? And break from L5, it means you're breaking from this block to the end. There is a while in a do, but this while is always true. Okay, so you have to break at some point. That's how while repeat is done. So it's kind of not obvious way to write manual JavaScript, but it's allow you to do any force control constructs in a JavaScript world. So this one is actually on my website, so you can go there and you can play it. It's all runs in the browser. It's all you know, just client side JavaScript. Okay, you say, oh, what the heck? Let's do ANSI compliance test, right? So just copy paste some text. Unfortunately, it's for some reason it's slow in the browser. It's half a second in command line mode, but it's several seconds in them. So while it's doing it, yeah, okay, so it's done. So I want to show you something. So this editor on the left calls code mirror. So if you're familiar with basically, so you can embed a code editor in your browser as standard that support more than 100 languages, including Force. So I wrote a plugin for Force, contributed to Code Mirror a while ago. And what it's doing is actually running tiny Force interpreter in it, inside the plugin. How do you see it? First of all, I'm not sure that so if you're on your machine, and you will see a difference in no. Okay, anyway, so the difference between when you're in compile stage, so between here and here, you will see background changing. So it's in compile stage. So by looking at the background color, you'll see it's in compile stage. So, and all the words defined here will be green here. So if you make a mistake or something here, this word will disappear. So the colorization is actually cascading, and next level of colorization done based on vocabulary that's already in the plugin. So of course it's know about some core words. It doesn't know about much about maybe some extensions or something. But everything that in the source code by the end of the day will do. And yeah, so after sometimes it's big, it's 1,000 line, and I haven't optimized it yet, but it's saying error in that line. That's different for interpreter. That's a real one. So okay, now it's green again. So this compliance suite, I have about 60 errors right now, but it's finishes, and it's giving me each dot here is actually a test passing. If test doesn't pass, it shows error and expected results and stuff. So I have some mismatches in in the flow. But as you can see, yeah, so I have some troubles with arithmetics. Because JavaScript don't have integer 64 arithmetics, right? So we have to have double arithmetic. I use a special library, basically simulating 64 integer arithmetic. But I still have some mismatches in mixed unsigned multiplication. I have to fix. And FM/mode, similar stuff. And yeah, by the end of this file, this report, I have a couple of errors too, but it is passing everything. So it defined all the words right way and executed them. There is some arithmetic and there are some mismatches, but I'm gonna. So you can run this thing on the server. So because it's stream, so it's meant for node, it's meant for server. So you can create a stream, you can attach input program stream into it, you can attach output stream from it, and it will be live. And you're allowed to have many of them in the same thread. Because if data interrupts, it doesn't consume CPU, it just waits for the data. It's in a callback. So it doesn't really consume CPU time. So this is one experiment. So as I showed you, there are some challenges. And one is, how do you organize force vocabulary in terms of JavaScript structures? So you have to arrange them in arrays, objects, all what's available. It's not like one memory array and you compile in it, right? There is no branches. It has to be organized in JavaScript this way. I found a way to do that. And complex control structures, as I showed you, have to break them in some machine, which, imagine a machine that has no conditional and conditional branches, like no goto, like basic with no goto, right? It's like weird, but you can do that. And I showed you how. And you have to use break from the block. And of course, create does magic, drives everybody crazy except probably me. I don't know, because I'm super mad. But I managed to implement many of those. So one other thing is JavaScript to force. How do you go this way? And again, I'm not going to spend much time on this, but there is prototype which takes JavaScript and compile it into force. Maybe next time I'll explain more in detail, but basically what you're doing, you write in JavaScript, you analyzing this code using abstract syntax tree and try to extract stack behavior of your choice. This is elaborate version, and when you compress it, it's optimized away a lot of garbage. So you can go this way too. So there is a project how to go this way too. So and the last thing I want to show you. Yeah, I can do, but it sounds like infinite loop. It's only Apple do it. Yeah, exactly. So the idea was actually write in JavaScript and run it on some microcontroller, right? Well, the way you do it, you translate it to force, and you run force system, basically. No, no, of course not. Because here, this is stack operation. I try to map some local variables into stack operation.
The break's coming up soon, so I recommend you ask your questions at the break. I wish we could give each of the speakers today, an hour that they deserve, but unfortunately, we're a little pressed for time. So
okay.
You're done.
Yeah. Okay. Thank you. Thank you. Again, everything on GitHub, everything open source. Welcome to contribute. JavaScript has nice package manager calls npm. node package manager, everything is there, so you can install. You can run it from command line as a force, as a REPL. You can stream through it, so it's basically all available. I'm working on compliance, so which should be done soon. Okay, who's next? Oh.
Oh, great, thank you. Oh, no, can you, and the screen on.
I think you can turn it here. You're probably going to have to connect with the computer.
Okay.
Reach out and push a button.
Yeah, but it's got to cool off before I can lower the screen, unfortunately.
Let's see.
Is there something special about your projector?
Yeah, it has HDMI. Well, I'll do HDMI.
You have a large size one that'll go on the wall?
Yeah, I got a long one.
Bring it up here. You want to bring your computer up here?
Okay, yeah. Good. Do. Okay.
Wish there was time for everybody to do sound check, you know.
Okay, try it now and see if we got it. Okay, so we're waiting for the projector to come up. Okay, she'll get started. She'll get started now. I can talk. Here you go.
Yes, go.
Okay, Bill Ragsdale here. The bio, I was a member of the original fourth founders, the 5 of us that founded Fourth Interest Group underneath the oak tree over by the coffee shop. In about 1978 or so, I led the fourth implementation team, wrote the FIG fourth model, was on the standards team, and then had a company for 25 years that did all the products in fourth. They were all in little embedded systems, doing security products. They were all written in fourth for 25 years. And I retired 20 years ago, and those products are still in use. If you go to Kennedy, LaGuardia, and Newark airports, Nashville, New Orleans, Denver International, you'll see our ID badge reader card readers on the wall. And at the Denver International Airport, there are 4,000 of them. And that put braces on my kids' teeth. That was very, very good year. We're killing time while we wait for the projector to come up. And we'll pray that HDMI gets into the system. All right, this is a project. You'll see at the beginning it says, listen to your heart. This is not a touchy-feely, existential, love your fellow man sort of thing. What it really is listening to your individual heart. How many people here have either atrial fibrillation or atrial flutter? Are we that healthy? Who's lying? Who's fibbing? The reason is that about 5%, 3%, 4% of all people have it. And at over about age 60, it increases to about 10%. And it goes up to at age 90, it's about 30%. My mother had it, and she died from it at the ripe old age of about 92. The risk is not from atrial fibrillation itself, but it's from the increased chance of stroke. Once you have atrial fibrillation, if it's untreated, your chance of stroke goes up 10% a year, cumulative. So that means in the second year, it's gone to 20%, the third year, it's 30%, the fourth year, it's 40%. And after 10 years, you have a very negative outlook. The historical treatment has been blood thinners like Coumadin, warfarin, and so on, but it can also be treated pharmacologically to cure it. The warfarin minimizes the chance of stroke. However, some pharmacological and surgical treatments can actually put it in abeyance or cure it. So we think we're getting onto the network here. Does
anybody use the HDMI on this before? What button did you push?
Whatever button you push, change the mode from DVI-D to video. So, yeah, you want to go to HDMI. Oh,
Have we got it?
no, that's
What was? Video was? I didn't see anything there. Are we likely to be putting something out at this time?
Yes.
Okay.
We'll give it another little couple minutes, and you can back up over to my projector. This suffers greatly if we don't have the video. There we go. Any improvement up there?
Is that you?
Oh, that's me.
Doesn't like being threatened with another device.
Okay, let's see if we can breathe a little spark of life into it here. That's good. That's good. Okay, we'll soldier on without worrying about keystoning and things like that. All right, so here's the beginning. Listen to your heart. First slide we've already gone through. The probability or the problem of stroke is that atrial fibrillation is a premature heartbeat and irregular heart rate, and it kills the heart efficiency about 30%. And what happens is you get blood pooling in the atria, the two upper chambers of the heart. The blood kind of swirls and pools there and tends to clot. And sometime, some way, the hot clot breaks loose and you have a stroke. So heart anatomy, we are all dependent on the sinoatrial node, which is in the upper corner of the heart here. A little thing, okay, up. There we go, it's right up there. It's about a 1 millimeter cluster of cells, and sets the rate for the heart. It puts out an electrical wavefront that goes down to the atrial AV node, atrial ventricular node, which receives it and then retransmits it down these two fibrous branches, the left and right bundle branch. And it is very electromechanical. In other words, the electrical impulses from the heart generate a wavefront that goes over your entire body. And they are measured from arm to arm, from leg to leg. It was discovered by Professor Einthoven about 100 years ago. And so it is amazing in that You know, you have an electrical impulse from arm to arm, which is a reflection of that waveform that is radiating out from your heart. Okay, it says, travels to the extremities. A very wide range of health conditions can be inferred from the diagram. Now here's the idealized diagram of the electrical impulse from the heart. You start out with the P wave, which is initiated by that upper little node. And then there's a transition as it goes from the atria, the AV node, the SA node down to the AV node. There's a little transition time. Then the lower half of the heart responds. Searching. Yeah. Okay. Okay. So then the ventricles respond with the great big impulse here, and then finally you have what's called repolarization, which is as the electrical wavefront relaxes and the heart polarity returns to normal. So there's the T wave, and then finally there's an almost invisible U wave at the end, which was hardly visible, gets lost. So here's your diagnostic EKG, electrocardiogram. The K is from German, from heart. In US, it's ECG, and they're interchangeable. Every text and every report it'll use ECG for electrocardiogram or EKG. The upper trace is lead 1, and for the discussion we have today, that's what the system you will see generates as lead 1. That is right arm to left arm. Lead 2 is right arm to left leg. And it is a better diagonal across the heart. So lead 2 is a little more revealing because it goes across the diagonal of your body from your right shoulder, right upper arm down to your thigh. There are, this is 12 lead EKG. There are about 10 different sub-diagrams that occur in this, and this has been simplified. So I had atrial fibrillation, I had atrial flutter. The atrial flutter was cured by heart surgery, non-invasive, but you know, they use a catheter, it goes up your leg, goes into your heart, they zap a few things, and goes away. But atrial fibrillation is not so amenable to treatment. So before we had an effective treatment for it, I wanted to know, was I having it or not? Now, frankly, you can just take your pulse and you can tell. But being an engineer, I wanted the answer. I wanted to have it nailed. So what did I need? I needed a portable EKG in my pocket. So I consulted our Lord and mentor, Steve Jobs, and said, Steve, could you pony up a portable EKG on my cell phone? He introduced it, but it was a fake product. In other words, the product did not exist. All we did was just glued the waveform over the front of a cell phone. So I had to build my own portable EKG in my pocket. Well, the front end is a differential low-level amplifier down in the millivolt range, and that was readily available. So I did a design. Oh, and by the way, this is a fourth non-fourth project. Okay, it started out as fourth, and then then the fourth went away. So my project design was, we start out with that input amplifier, go to an automatic level control, then to a microprocessor programmed in fourth, and then into Bluetooth, then connecting to the cell phone, Bluetooth to the display, and a report. The barrier I ran into was how to connect what originally I chose Bluetooth, how to connect from the peripherals into the phone. And I found that at that time, several years ago, the Bluetooth was highly protected secret, couldn't touch it, couldn't talk about it, had to reverse engineer it or whatever. For extra credit, how many ways could I have used to get my data from a peripheral into the phone? What all ways are there? Huh? A wire. I could hook wires to it, to the auxiliary connector. What else? I could use Wi-Fi. What else? I don't know about infrared. That's way beyond my skill level. Yes. The microphone. And also the one we missed was the 1/8" audio video jack on the top. Okay. Guess what? Okay, so based on that little roadblock and my unfamiliarity with getting into the iPhone, the project languished for a while. Meanwhile, I found a treatment plan that worked for me, and so the priority was a lot less. Then, after the pause, guess what? Commercial success. A company came out with exactly what I had envisioned. It's a case that goes around your cell phone, and it contains the electronics, the front end for the EKG. And most innovatively, they use the audio input. So you have non-invasive to the telephone. You don't have to know their formats. You don't have to have any wires. You just do it because the phone itself digitizes the audio stream. So they use a 19 kilohertz analog subcarrier. Oh, and so the question is how to get into either the cell phone or into an iPad. The commercial company did it with a 19 kilohertz audio FM stream. Now, I've shown here a digital zeros and ones FM stream. It is not, it is pure analog. Okay, so inside the phone is nothing but inside the adapter is nothing but a low-level millivolt amplifier and then a simple FM modulator, and all the rest is done inside the phone. And this is an actual snapshot of the telephone waveform in use. In other words, when you operate through this on your phone, you see exactly that trace. They also maintain a database so that your EKGs go into central database. You can send a link to your cardiologist. He can look at it anytime he wants. To get this originally, it's FCC approved, which is essentially revolutionary. That you could get it through FCC, in that, of course, it's non-invasive and is it safe and effective? Yes, it is. Originally, it came out as a product. Yeah, FDA. Right, it's FDA approved. So originally, it came out. It was designed by a doctor engineer maybe 7 years ago. Before approvals, he put it out for veterinary use. So you could actually kind of buy it and pretend it was for veterinary use, and you could still use it. Then they went through a level which you had to have it on prescription by a doctor. Well, it turns out my daughter at that time was and is a doctor, and she was just in training, but she has her doctor number. Now, every doctor has about a 13-digit number that is their doctor number, and so you had to turn the doctor number in to buy the product, which I did. So then I got essentially, not quite a beta, but I got a very early production. About 6 months later, 8 months later, it was approved by FDA for over-the-counter use, so anybody can buy it anywhere, anytime, and it's like $85. Now, if this was released through the medical profession, it would probably be $800, but it's $85. Send your credit card number in. The printout, if you have a PDF generated, is this form. And notice it's lead 1. It is only that first waveform, which is slightly less informative. But to generate a lead 2, all you do is you put one finger on here and put it on your bare calf, and now you have a lead 2. And it's slightly more informative. Oops. Okay. How are we doing for time?
As much as you want.
We got 5 minutes?
As much as you want.
Oh, what? No, I don't. Okay. No, it's fine. Okay. We'll need like 4 or 5 minutes. All right. Now, one of the most astounding things that I discovered just in messing around with it, because you get that audio link, it means that it's a one-way transmission from the sensor device into the iPhone, but it also goes to the iPad, so you can do both at the same time. So I believe now, with a little bit of luck, I'll be able to do a live EKG. I'm wiggling my fingers.
They actually send these to interpretive center.
I had the phone backwards. You're supposed to hold the little button on your right side, not your left. Let's see. Classify. Okay, let's see. There's a little invert button somewhere.
You're upside. You're right side up. It looks like.
That's upside down, but there's a. Let's see.
The text is right.
Invert. There we go.
And plus.
So there we go. Okay. Which is quite reassuring. Occasionally, I used to, I don't do it anymore. You know, when I was so proud of this and I'd walk around with it and I'd talk to techie guys about, oh, yeah, I'll do your EKG. So I've had some friends that, you know, we do it on and I look at it and I say, oh God, they're in deep doo-doo trouble. Because I've gotten where I can read the EKG, you know, fairly moderately well. But one of my close friends has had heart surgery and a valve replacement, and and he says, "How's it look?" And I said, "Oh, it looks okay, okay." No, it's terrible. But anyway, no, I can't tell. And when he's 87 years old, I can't tell him. So
I think the only thing you can tell him, really, without getting into serious trouble, is you need to see your doctor.
oh yeah, well, he's under intense care because he had a heart valve.
But
Yeah.
just random stranger.
Yeah.
The only thing you can tell him is
Yeah. Oh no.
you need to talk to your doctor.
No, I wouldn't even do that.
The other thing is practicing medicine without
I know.
license.
You know. I know. I know. Even with that, I mean, they say, "Why should I see my doctor?" I can't tell you. No. Yes.
Try putting them in your scalp to see
Brain waves. I think they're much lower level, and you're in the microvolt level, and then you've got to go. Are they? Okay. So what we see is they've done a beautiful packaging job. The first one that I got was for this, I think, what, iPhone 4, and it's integral, one piece all together. After that, they came out with all the variety of different packages, cell phone sizes, 6s and so on, and iPads. So the way it works actually is the little electrode portion is on a little subplate, very thin, you know, about a meter or less thick. Little subplate's got a battery in it, and then this case snaps around it. So the one insert, so all they have to do now is retool the outer shell. And so for the same price, you pick up a little case for your cell phone. And then to go on the iPad, they have kind of like a little sticky thing you just kind of stick on the back of your iPad. So, see that. So that concludes my formal remarks. Are there any questions or comments? Yes, Dave.
I recall in the early 70s, they had a device that you could use at home, patient could use at home, that you applied electrodes and it went to a box, and then you put the telephone on it, and electric motor, and it produced FM modulated tones. And you called your doctor, and he would have the decoder there,
Oh.
stuff like that. So that's
Where for that remote diagnostic has been around in various forms, heavily used in remote areas like Alaska. You know, if you're 200 miles from a doctor, this is a godsend to know what's going on, and the doctor can look at it. Let's see, I had some of the little thought, but that kind of went away, whatever it was. So anyway, right now it's, you know, it's somewhat more of an amusement than it is for scientific use on my part. But my cell phone goes off twice a day, 10 o'clock in the morning, 10 o'clock at night. And I use the EAS warning from the, you know, the Weather Service on tornadoes. And so that little alarm goes off on my phone, and people say, "What's that?" And I said, "It's time to take a pill or die." So we've got, you know, my problem under pharmacological control. So thank you very much. We'll see you through the rest of the day.
We're going to shorten the break a little because we're really late. But if you haven't signed up for lunch, you're going to go hungry. Seriously, Dave, do you have the list now? All right, it's in the back of the room. All right, the list is, find the list and sign up now. We're just about to order lunch. Yes, I could have fooled me. Okay. Break. Coffee, bathroom, all of that stuff.
Good. Thank you.
What happened was Star Trek told me I needed to get Star Trek. But anyways, the disease actually, well, I don't know how to break this to you. This is the least.
Yeah, I was.
Dave.
Oh, are you? No. I just was trying to check to get the image.
Oh, that's what I was going to do too. So I'll wait for you.
Okay, no. You go ahead. You do it, and then it'll work for me as long as you're using HDMI. Right. Oh, you got VHS. So
The VGA, yeah.
Is that a? What is this connector?
This is mini display port.
Oh. Yeah. So maybe it isn't. That is it. What is it?
It changes the resolution on my screen, so I know that it's. Oh, maybe the screen. Well, hang on. It's got to go through its. There we go.
Oh. Oh, maybe that's what it's. Yeah, maybe that's what it needed to be all along.
Okay. So that
That's
says
the laptop.
that says laptop. This is HDMI.
I wonder whether. Let me try this for 1 second just to see whether it. Oh, I think it's good.
Well, I just unplugged mine, so.
Well. Yeah, what is it? It seems something. There, okay. I can get it. Yeah.
Excuse me.
Okay. That would suck.
So that's what we do in the compiler.
What's the source?
It's like like subset with annotation, guided
Are you using an ally?
I do Ally. It's kind of similar in the sense that they also use search to do scheduling to find like the best schedule to provide like the fastest schedule. We do search to also like optimize instructions, right? Like, can I use different instructions? How can I schedule? So it's like combined, like scheduling of instructions and also instruction selection.
So something that was bothering me about this two variation functions, and I feel like it really hurts my head is thinking about situation where these schedules would seem to be very sensitive to the underlying behavior. Is this something that, like, with green array, you have the continuous tracking? It seems very deterministic.
Yeah, I think the green area seems easier to deal with because really simple. So it's definitely easier to model the performance, especially when the model you have. Like if you try to model like 86, it's like a hidden array. So that's why it's like pretty suitable for the compiler for reading in that sense. But like this technique also works in like more complicated machine like like the prediction is really hard. So what people do is that you can like generate different variants. So like you can have some cost model to model like the cost of each instruction. And then you get like a approximation, right? And then you might like generate different variants that have like good cost and you actually try that on the machine.
Right, and then maybe switching the profile.
Yeah, so I will talk about that compiler a little bit.
2-minute warning.
Very nice to see you again.
Yeah. Are you using Red X?
Not much. I think it's interesting to know. Yeah. My advisor was like, yeah, you should go and build like a new compiler. I haven't gone to that stage yet.
I've been looking for a semantic keyboard that seems like there's a little bit of work, but I don't know, maybe.
So I think I'm part of the section. Yeah, so I'm gonna keep like doing talk and the undergrad work, you're gonna keep a talk. Yeah, so I'm like gonna do like overview of the strategy build, and then like some technical and then really give some pleasure to my education operation. Okay, yeah, it's interesting. But also like build this new machine to like oh, this is very with like what model.
Okay. Yeah, so it's like, yeah.
Yeah, it was like, if you try to like read a solver that to do some application. Right now we can now do that solver, but we haven't like finished doing application.
Okay.
Yeah.
All right.
What's your name again? Sorry. Not yet. Except that my advisor. Yeah. So I can't go there.
Does anybody know how much time we have before the break's over?
Oh, about -7 minutes.
Oh, -27. Are you ready to go?
Just about.
I'm ready.
Is this thing on?
You have signed up for lunch by now, otherwise you'll be very hungry. If you've got money, there's a pile of money in the back. The donuts aren't free, the coffee isn't free.
Yeah, dollars to donuts used to be long odds. Now it's always
Sure, why not?
Do I have audio? Are green bars moving? I have bars moving. Excellent. So audio check is good.
All right, Sam, you're on. Everybody else, take it outside if you're still talking.
All right, everybody. Hello, everyone. Hope everybody is doing well. I have my little script here because, of course, I didn't practice anything. But I'm happy to speak for another fourth day, but I'd like to talk about, in this case, automated testing. And in particular, how I apply the techniques towards a particular project that I'm working on. Why is this not automatically moving? You should be over here by now. On the Kestrel 3, which is a homemade computer of my own design. It's open source, open hardware, and eventually it will have a fourth interpreter in ROM that you can just drop into if you don't have any other bootable sources. But before I talk about that, I need to talk about what is a test, and there's 4 parts to a test. You have the setup, where you establish your environment. You have the functionality that you're actually invoking. Then there's a section where you actually assert the results, and then finally you clean up your environment. In fourth, we often emphasize interactive testing over automated testing, but unfortunately there are some problems with that. In particular, you can only keep 7 things in your head plus or minus 2. Right? So to make up for that fallacy, you definitely want to rely on automated testing. It relieves the software engineer of the mental burden of making sure that your interactive tests are repeatable. And there's 2 types. You have built-in self-tests, and then you also have something called unit integration and systems testing. Now, these tests sit outside the deliverable, whereas built-in self-tests sit inside the deliverable. I'll show an example of that a little bit later on. Testing in particular, especially automated testing, it's not a universal given, but it is mostly universal. Typically, if you can test interactively, there's a 90% chance that you can automate it somehow. Let's see here. So one of the benefits of testing is that it is reproducible. Basically, you want the reproducibility so that you can, after you make a change to your code, you want to make sure that you actually are fixing the bug that you documented. And speaking of documentation, tests serve as great examples. So if you forget how to do something, you can just go back to a test that you know works and actually look at the code for that. Reduces coupling. If you write your code so that you emphasize testing, you find that you write your code in such a way that it sometimes even inconveniently, it's actually modular to the point where you can actually just pluck it out and just drop it into another package pretty much verbatim. And of course, it enhances cohesion, which basically, as a result of being able to pluck it out and plug it in, it's code that does one thing and one thing very well. There are some problems with tests, automating tests. It is a separate code base that you need to maintain, which implies that there are economic decisions that you need to make. However, experience shows that the investment in making testable code pays off in a very big way. And there's plenty of literature on that. Code coverage is another benefit. If you have automated testing, you need to make sure that that your coverage is appropriate. Otherwise, you're just pretty much wasting time. And the way that you write these tests is, going back to Mr. Moore's adage, you factor, you factor, you factor some more. I did mention that at times writing modular code is occasionally burdensome. If you can't test your code, it's because you didn't factor enough. And that's pretty much the fact. The whole point of testable code is that you want to ensure quality assurance. You don't want to constantly ask yourself, why is this thing broken, right? So QA versus Q&A. So Previous 4 minutes I spent discussing or briefly going over the theory, but what does it actually look like in practice? So what I'm about to do now is I'm about to show some code examples from the Kestrel. There are 2 examples that I'm going to draw from. The first is the 4th interpreter that will eventually show up in ROM. The second example will be a simple operating system that I'm writing. I am, of course, targeting 2 audiences at the same time with the Kestrel, one being non-4th people, other people being 4th. But we will start out with the 4th example first. I'm just going to skip ahead here. All right, so basically, this is written in assembly language, as you can probably well tell. This is one of the tests. This is actually the first half of the test. And what it is doing in this top part here is establishing the operating environment in which, for the code that we actually want to try, which is this try unsigned number. So what we're doing is we're setting the base to 10, and we're setting input pointer, if you will, to the origin of the number. Now, in order for us to actually do the conversion, we actually have to multiply some numbers. The problem is, at the time that I wrote this test, I don't actually have a multiply routine. So I actually had to hand code the multiply routine that eventually would have plugged in, but didn't have just yet. So I needed some form of runtime polymorphism. And the way that I did that is every test has a vector table, or a jump table, if you will. There's a function in the tests called setVex, which sets a pointer to that table. We then define in the assembly code functions that actually dispatch through that vector table. And in this particular case, we have several types of multiplication routines, because after all, we could also support hexadecimal numbers as well. It's not just decimal. So once we have this environment set up and we've set our vector tables and we've accounted for our runtime polymorphism in assembly language, which is not an environment you typically associate with polymorphism, we then run the actual conversion, and then we actually do our assertions. So here what we're checking for is that our word index is at offset 3, which means that we process the 3-digit number, and that it equals 1, 2, 3. And if any of those asserts fail, it will fail hard, by which I mean it will print out a diagnostic on the screen. It will then shut down the emulator, and if it's not running in an emulator, it will actually deadlock the machine. So no matter what, if something fails, you know it immediately. There are numerous tests associated with a typical test suite. And in this case, these are all related to numeric conversion, as you can tell. So what happens is when the environment boots up, it'll jump to start tests, which then calls assert boot. Now, instead of using the normal return address register for normal subroutines, although I could have used that, I'm using a different register, A0. It's an argument register. That A0 then will contain a return address that points into this data structure here. So the assert code knows from the very first word up here that we have 5 tests, and then immediately after that is pointers to all the test procedures that we actually execute. One of the things that I wanted to show, you'll notice that the test procedure starts with what I call a grep tag. It's basically something that I can say, oh, there's this tag in the output. Let me grep the source code to look for it. Since assembly code doesn't have associated line numbers, this is probably the closest thing. So if a test fails, I know I can at least identify where the start of that test actually is. So here's the definition of assert equals, and it's kind of wordy. It's an accident of history, I'm sure. But it basically does what you would expect. At the very top is an instruction that says branch if equal. And if everything is equal, we skip all of that code. We just return straight to the test. Everything else is basically preserving existing environment so that we can print out various messages such as expected blah got foo. So this is kind of what it looks like when you actually run the actual test run. You'll notice there's some diagnostic stuff up here about how it builds. We kick off the RISC-V architecture emulator, and then we see that it prints out the names of all the tests that it actually runs. If any one of those tests fails, the emulator will quit with a non-zero result code. So you can actually use this in not just automated testing, but even a continuous integration environment. So you could, if I were to develop this sufficiently enough, I could actually have it so that if anyone submits a change to GitHub, it will run these tests automatically, and it will go green or red status indicator, and actually email the appropriate parties as soon as anything fails. So onto STS, which is the name of the operating system that I have. This is a little bit different. This is not unit testing. This is built-in self-testing, which is kind of like unit testing, but it runs as a physical part of the package being developed. Now we're going to look at something that's more or less fourth code. You'll notice this word self-test, and it just launches exactly the same idea here. We just launch a bunch of tests. The only way that word returns is if all the tests pass, and if any test fails, it will die in a fiery ball of flame. So here's a simple file system test. So I've got open directory, I have open file tests, and then I've got something called loadseg. Loadseg is actually the simplest of all of those tests. Basically, it's responsible for loading a binary blob into memory and setting it up as an executable program. What I do, however, is I load, I've got a setup routine, I've got my cleanup routines here, and then in the middle, I've got the same basic structure. I invoke the function under test, and then I assert that what I'm getting back is what I expect. This is the current implementation, or at least the prefix of it, for loadseg. We open a file, we determine a file size, we allocate a block of memory that's sufficiently large enough, we read in the blob, et cetera, et cetera, et cetera. One of the things that you'll notice here is a lot of 2Ds and defroms and defetches and blah, blah, blah. This is an artifact of the RISC architecture. Trying to code in forth on a RISC architecture is problematic at best. If you make it a pure fourth, it will run horrifically slow. It's doable, but you'll be executing so many extraneous instructions that it negates the benefits of having the RISC architecture to begin with. So what I do is I have a separate evaluation stack apart from the data stack and the return stack. So 2D and from D and stuff, these are accessors to the in-memory data stack, and then the compiler maintains the in-register view of data stack as a separate entity. That's why you have all that noise. That's also why I started with the built-in self-tests, because maintaining stack balance between all these three entities has proven to be challenging. And strictly speaking, this isn't fourth. This is a dialect of machine fourth, which I call BSPL. And I'm using it as a statically compiled language to help bootstrap the development process. And there I just explained a little bit about what all those 2Ds and defroms are. So that's about it. Basically, the key elements here are that the emulator has a means of programmatically terminating itself with a result code that external tooling can detect. I have an assembly language assertion package that I use to verify expected results. And then I have a kind of an ad hoc convention over configuration style of a test framework that I use to actually run everything. So everything's up on GitHub. I also have the Kestrel Computer homepage website there as well, if anyone's interested. I know we're running short on time, so I'm going to end it here, but yeah, that's pretty much it.
I just want to make a comment. A comment. I really like the way you laid that out.
Oh. So it's a web templating engine called reveal.js. It's and had I practiced the speech more than work would allow me, if this would have flown a lot more smoothly. But let me just real quickly. Let me just show what some of these tests actually look like when we actually run them. Oops. Let's try running the correct results here. All right, so basically, we do a memory test, we do a call test, basically verifying that BSPL can actually make polymorphic calls, which is a necessity for the file system, string management, various types of objects that I'm working with, and then pretty much it drops immediately into the shell environment for, and we actually have the ability to run programs off a disk. This basically took me about 2 months of effort to get to this point, working an average of 2 to 3 hours on Saturdays. So however much man time that is. Seems like a lot of work. And compared to a straight fourth environment, it definitely is a lot of work. But if we go into fourth, so now we're actually running the unit tests. You'll notice that because these are unit tests and not built-in self-tests, it has to compile everything separately out of package. And then once it runs, everything dispatches, all the core functionality works. I now have a point. I don't have an interactive shell for fourth yet, but it does locate words in dictionary. It does do numeric conversions, and it does manage the data and return stack. One of the reasons why I haven't used BSPL for this, everything here is written in assembly language, but one of the reasons I haven't used BSPL to implement fourth to help speed up development is because this fourth caches top of stack in a register, BSPL does not. So that one simple change makes interop between the two environments kind of hokey. So, you know, not hokey, just greatly inconvenient.
If you have questions for Sam, you can ask him at lunchtime. I'd like to thank him and appreciate his patience with my giving him the hook.
Yep.
And Sam?
Yes.
I also want you to come back another time and give a more extensive lab on this particular subject because
on the automated testing? Yeah, the automated testing is, it's actually a deceptively simple topic, but I'll be happy to do that.
Great.
Yeah.
I wanted to address that all of you, if you have PowerPoint slides or other material that you want to share with posterity, send it to Dave. If you don't know where Dave's email address is on the website, send it to me. If you have other material that pertains to Fort that you want to preserve for posterity, and you're allergic to GitHub or other, you know, once again, you know, there might be a place for it on the website. If it's actively being developed, I suggest you use GitHub or some other similar thing because we don't really support continuous change. We've all grown old and ossified, I guess.
Hi everybody, Brad Nelson here as I frequently am to talk about fourth haiku. Quick run through for those of you unfamiliar with fourth haiku. The idea is tiny programs going to beautiful things, and the particular method to my madness is that I take a fourth-like language, convert it to JavaScript, and run it in the browser, and in some cases convert it all the way to a WebGL shader, so it can run really fast. And the main idea is that it there is a website that lets you share and evolve things collectively. Looks sort of like this. The idea initially was just that these were graphical haikus. It's a very simple dialectic fourth, no variables, no loops. A floating point data stack and return stack because that fit nicely with JavaScript. It's run once per pixel. You're given an X coordinate, a Y coordinate, and you're expected to give back red, green, blue, and potentially alpha. So the nice thing about it is it lets you go from a very small program like this. In fact, this one is actually a true haiku, 575, to something like that. And I think that's pretty exciting and neat. Animation can be added in a fairly straightforward way. You provide time as another parameter, and I do time in seconds because, again, floating point, so that was convenient. Animated at 30 frames per second. A lot of work to convert it to a shader, but that means that you can take something like this. This is created by Manwei, one of our very prolific users. And I should say, by the way, a lot of the haikus that I'll be showing are produced by my users, whom I'm deeply appreciative of. And they put a lot of interesting work. Many of them are demo sceners, and so they compete over exactly how small the program is. They care about every last byte, so they'll do things like redefine dupe as D just to make the program smaller. A program like this can turn into something like that. Or even smaller, tiny little 125 byte program like that turns into something like that. So I thought I'd talk about all the fun things that have gone on in 2015, at the end of the year. I foolishly, towards the beginning of the year, gave a talk entitled Haiku Monthly. Nominally, the idea was it was going to be like a little news broadcast or something. That was the conceit. Of course, this put me on the hook to actually do something every month, which I nearly approximately did. So there was, yeah. It was good. Well, anyways, I gave Kevin some content. So what all has happened with this? We also got more users. We've got some users now from SVFIG who've been contributing haikus busily, and many of the haikus are actually labeled in Chinese, and so I have no idea what they are about, and it's kind of fun to see them though. There was a wave of spam. Suddenly the spammers discovered my site, and I had to put in mitigations to protect it from the onslaught of people submitting, or actually bots submitting bogus haikus with random garbage text and whatnot. You can actually look at the traffic logs and see the spam rolling up against things. I added word search finally. It got to be that there's so many haikus that finding them is tedious. So initially I added a very rudimentary form of word search, but now it's full word search. So for example, if I wanted to look for Mandelbrot instances, I can now search for them and see, oh, here are all these various Mandelbrot things. Or let's say I want to search for Mario, and oh, here's Mario, right? So lots of fun there. What else? So at Dr. King's prompting, he asked the interesting question of why no if else then. I had gotten by for quite a number of years actually without if else then. And of course, in trying to explain to him why it was so hard to add, it convinced me that I could add it. I'm not sure it actually necessarily makes things better, but it's interesting to have. There's a separate talk that you can undoubtedly get the video on the details. But there's some tricky problems. It's not a general if else then due to the constraints of turning it into a GL shader. It requires that the two sides are balanced in terms of the stacks, which is somewhat limiting, but okay some of the time. I cribbed a feature off of there's a site called Shader Toy, which actually has a a certain resemblance. I was unaware of them for many years. It's actually similar to Fourth Haiku, except if you can imagine, these are haikus directly in WebGL shaders, and so it's C code. Needless to say, they're not small programs, they're big programs. But they had one neat feature that I thought was very cool, and I decided to add this, which is that when you float over an animated item, it immediately kicks in, and so that got added in and does fun things. And so you can preview a haiku without actually going in and clicking on it, which is kind of handy. Let's see, what other fun? So I did an exploration of haiku genealogy. I made a foolish mistake early on with the haiku site. I never anticipated quite so many people submitting them. Someone in early days suggested the idea of allowing you to create a derived work, and so you start from someone's existing haiku and produce a new one. What I failed to do was record what you had based that work on, and so I was left with a pile of haikus that had some kind of genealogical relationship, but which unfortunately I didn't know what that relationship was. So I came up with a technique for me to make an educated guess with them, and so I did some approximate string matching and culled the database and actually tried to backwards derive the genealogy in the way that you might with looking at DNA or something of the sort. And so now in the database, all of the old haikus are labeled in instances where there appears to be a relationship with them as possibly based on so-and-so. And I've started recording what you used as the starting point for the haikus. So you can now get some idea of what came from what. And there's an interesting talk in that. For a long time, I had the problem that I didn't particularly want all the spam of people contacting me. And so I didn't have any contact information on the site. And so the standard technique for people to try to get my attention was to post haikus, sort of saying, hey, Brad, something's broken. And in some cases, they still do this, actually. They'll have the flashing red haiku to grab my attention. But they would also do this to communicate with each other, which was very roundabout. And so I went ahead, and there's this lovely company, Disquist, that provides the plumbing to very easily add a forum to your site. And so now at the bottom of every haiku, if we, let's say, go into Pac-Man here, there's a forum that I didn't have to put a whole lot of energy into to adding, and yet it lets my users communicate with each other directly instead of not spamming up the database of haikus. I did some more experiments with sound, and that's actually one of the things I'm going to show off briefly today. And very recently, I've done some experimentation with interactivity, something else I'll talk about today. And lastly, state. This is something people have been asking me about for a long time. Up until just a short while ago, the haikus were stateless. They were just a thing that you could view in time, but they didn't actually have any state that they could accumulate. I've added a little bit of state. I played with making a kiosk, and later on I will actually set up a kiosk in the corner there. Folks can come over and push on it. So I did a little more experimentation recently with sound, and I'll just tell you the sad saga of my attempts at sound. Sound is actually much harder than images. It's very easy to splash up some colors and say, oh, that's beautiful, right? Whereas sound, if it's cacophonous, you're out of luck. So my first attempt at sound was just, well, I'll just pick some pixel on the screen and I'll associate that with an audio signal. Just sample in the corner. But again, cacophony is easy. And also syncing with the animation is very hard. You think, oh, this picture looks great, but imagine you want to have some portion of it oscillate in some form and then match that up. It was just ridiculous. About as far as I got with these was, putting in simple kinds of waveforms, telephone sounds, dial tones, things like that. So my second attempt was I took two sample points, and one on the left and the right side, one for the note and the other for the volume, and then I mapped this to a pentatonic scale, and this has solved my cacophony problem in the sense that I could now produce haikus that were not as cacophonous, but unfortunately they all kind of sound the same. As you'll see here, I'll play one of them to give you an idea. I do not have it. It's not looking at it. So so anyways, it sounds like a sort of a maybe an Asian sounding flute, and unfortunately there's some possibilities there, but they're still very hard to sync with the animation. I mean, if you put up an arbitrary haiku, when I first did this, people would say, "Oh, what does that one sound like?" And the trouble is that unless you kind of carefully arrange things so that those 2 points on the screen are doing the right sort of interesting things, it doesn't sound like much of anything. You have little bleeps and chirps. And so this is where it's at for a long time. So finally, of course, people have suggested this for the longest time, and I somehow was dense and wasn't hearing them. And just add another word for it. And that was sort of the obvious thing, to have an audio word that takes an input and use that as the sample point. And go back to that raw audio, because people are actually very clever and hopefully can do interesting things with it. And the great thing about having a word that's dedicated to producing the sound is that now I can notice, okay, well, you've used the audio word, so I can tag the haiku as actually having some sort of interesting sound. And so it's early days with this in terms of how people may come to use it, but let's do some. Let's take a look here. I should just search. Use the search feature. Okay. So let's see. So for example, you can do something like this, which is very simple. And here the audio portion is sort of vaguely related to the image. Not very interesting in and of itself, but there's. Oh, actually, let me go. What is that one called? Let's see. We want. So some people, of course, have used this to produce terrible sounds. This is going to hurt. Yeah, let's not do that. So there's the danger with what's.
Was that on purpose?
That was somebody did that on purpose. Yeah. Let's see. So here's one that is sort of a little better. Interesting things there. Oh, that's terrible. Okay. But when you combine this with the interactivity, which I'll talk about later, you can do some interesting things. Oops. Which is vaguely amusing. Or you can try to do something so anyways, mixed experiment, but the nice thing is that just as I was very impressed that I never imagined that folks would, for instance, put Mario in the haikus, the same technique that's used to embed some data can be used to very carefully embed music data. So you could do something. And that's not quite right, but let me, so that was with a sine wave, but of course what you really want to do, I'm going to turn that sine wave with a little 0 greater than into, whoops, we got into a square wave. And the notes are still wrong because I got the notes in the wrong place. But anyways, there's the potential there, and my hope is that my users will in time find interesting ways to make use of that, given that they now have the power in their hands to actually do the audio directly. Because what I should have mentioned before is that Sound 1.0 with raw audio, I took that out at some point because I found it disruptive and cacophonous. But this way, it's isolated. You know somebody was at least trying to make something interesting sounding. So interactivity, let's talk about that. So interactivity, I came to a strange way. This is another one where people have been kind of suggesting this for a while, and I just haven't heard it. I had this vague idea that I wanted to do something physical for Fourth Day, and the thing I wanted to do didn't pan out. And so, well, I was inspired by Charlie Shattuck had this lovely steno keyboard, and I'm not a hardware guy, and I'm terrible at it. But I thought, hey, I want to do a steno keyboard. Let's make the easiest steno keyboard I can. And so that I'll talk about that in a moment. But that was what got me here. But anyways, that made me realize, hey, what I really want is actually all kinds of inputs, a mouse and keyboard. And so buttons are my steno keyboard was the starting point, so I have a weird sort of a keyboard with 23 buttons, and so you now have the buttons word, which will give you a number with each bit position of each is 23 bit positions as a bit for various buttons, and there's also the button keyword that lets you pluck out a single one for convenience and get a flag out of it. Let's get a little demonstration of that. So this is we'll talk about the steno keyboard in a moment, but it's hooked up to the steno keyboard, but it's also hooked up to the regular keyboard. And so folks have done all kinds of fun things with this just in the very short period of time since I've added it. Let's actually search for button. So for example, well, actually this one's mine, but let's see. So you can now control and drive and jump for whatever reason. You can, if you want to move around the flagpole, someone in Taiwan has helpfully added this, or raise the flag and surrender. You can move around a flame. And what else do we have here? Okay, you got a moving rectangle with a wiggle here, and we'll get to some others in a moment. All right, so that's the buttons, and of course, mouse is fun. This was sort of more obvious and straightforward. I just provided 2 words to give you the current mouse position. It's in the same coordinate space as the rest of the haiku, but it's allowed to extend outside of the area. And one extra embellishment is that this works as a web app, and so it works on it actually works on phones as well and touch screens. And this laptop has a touch screen. So there's sort of two modes of operation to this. So if I look for mouse, whoops, that's not. I want to look for the word MX. So let's see. So for example, now you can track around with the mouse and have the tunnel follow. It's really fun to do it with the touch screen though, because then you can touch it and wiggle around. You can, and there's lots of variations in this sort of thing. Move the object around. Let me find the raw. So this, you also have the button. The way I decided to handle mouse button is to make it synonymous with button number 0. I only support a single mouse button. When you push it down in the sample, it's there. The question, of course, is how do you do that with touch? With the APIs of the web for touch, you can detect whether or not you support multi-touch in the device. If you don't support multi-touch and you touch down, that's considered both a press and a mouse event. But if you have multi-touch, and you can touch with 2 fingers as the way to click, so you get that sort of operation. Let's see, and it's I encourage you later with the kiosk. Which? The whole mouse package. No, the mouse was actually relatively easy. In fact, the hardest part, and I'll talk about this in a minute, was actually state. Here's color. So 0 for click. So the other thing that fell out of this kind of naturally and was interrelated was state. Up until now, the haikus have been stateless. And the problem of actually getting the mouse input and the button input in was actually very closely related to state, because when you're running these as GL shaders, GL is fanning these out to a multi-core GPU, and it's doing a lot of the calculations for each pixel separate from each other. And so there's not a lot of direct coordination. And so I needed to restructure things so that I could broadcast out the state of the buttons and the state of the mouse and that sort of thing. And in the process, it dawned on me that I could also support a limited amount of state that's shared between the entire haiku. And so this let me bring back load and store. But unfortunately, memory is a little tight. I have a total of 16 memory locations. This is a concession to the GL shaders. Basically, I don't have any way to assert that I'm definitely not that I'm blasting the right amount of data to the shader. So for now, this was the compromise. The way it's structured, remember, you've got floating point values everywhere. So it's 15 locations. It's floored and modded, so it wraps around in all kinds of fun ways. But it's enough state for a few things. The key thing here is that this runs actually not in GL, but it runs actually in JavaScript at a particular pixel location. And then the result is broadcast out. But of course, if you have load and store in your Haiku, this actually also happens at each pixel location. So I had a little problem because it's being dispersed in each pixel. My solution was to add DT. The idea here being that you need some way to know. Typically, if you're animating something, you want to know how much time has passed since the last frame. If you do this, it lets you solve the problem of how this state is manipulated, because in the GPU, you'll just set DT to 0. And then in that one pixel location, you'll run it with some actual change based on what the frame rate currently is. And then that result will be found out. So first run with some real DT in that one location, and then that gets broadcast. So it's a little weird. If you expect at each pixel location to have a separate 16 values, you'll be disappointed. But it has the virtue that you can sort of use load and store in a somewhat normal fashion. And generally not think about it unless you hit some fun edge cases. So that opens up the door to all sorts of fun things. And in fact, my user community has impressed me. Well, I forgot to show this one earlier with this is a fun one with the mouse. But anyways, by far the coolest use of state, it's actually going to be hard to look for load and store, because there's this lovely idea of stop words in search engines where you don't actually search for certain words if they look like punctuation. So load and store are right out. So actually, I cheated already. This one, for example, is keeping the state of where you're at side to side in a variable. If you look down here, it's there's some manipulation, and you'll see that DT is actively used. If you didn't use DT, you could imagine using some fixed time set, but then the speed of the Haiku would vary if you're not careful. So I highly recommend DT. By far, the coolest one to show up so far is this. So you've got, he's actually got the. So, definitely fun, and it's amusing because it's not that big of a haiku either. That's the whole program right there. So, anyways, so that's state. Oh, another fun one from our Taiwan users. This looks very primitive, but what this actually is they've got the logic for jumping here. So if you jump up on top of that, it's there, and then gravity kicks in. So there's just a little bit of state. So fun stuff. One thing I found in the so another embellishment, you may have noticed suddenly that there's a lot of little icons on the site. The haikus are labeled with them, and rather than go and whip out the image editor, I was able to have a little fun with Unicode. If you find yourself in need of an icon, I highly recommend the very extensive set of emoticons that are now available in browsers. And so I didn't have to find a search icon. There actually is a character for search that gives you the magnifying glass. I now tag the haikus with their category. So animated haikus are no longer tagged with a little A, but rather a little movie camera. Interactive ones have a game controller, and there's you can be either interactive or animated, but not both. And then haikus can have audio or not. I also changed a lot of things that were text to little icons for play and pause. Oddly enough, if anybody knows a solution to this, you would think with all this range of symbols out there that there would be a convenient symbol for pause in the Unicode set, and yet the one that's there is apparently considered to be kind of a mathematical symbol. Not all the fonts have it, not all the browsers have it. And so I'm actually currently doing pause as 2 bars, and even the 2 bars don't look right. They look different in each browser. So, okay, thank you. And of course, I changed love and there used to be a voting button for love and hate. Amusingly, when I went and did this reformat of the page, I thought, well, I don't really, it's not nice to say you hate somebody's work, and so let me get rid of the thumbs down. But less than a day passed, and I had my users saying, "Bring back the hate." You know, we need to. There are some of these haikus have got to go. So they insisted that I bring back the. Down and they posted haikus saying, "Bring back the hate." So anyhow, what led me here is the Steno keyboard, and this was motivated by me. Bear in mind, being terrible at hardware. I'm a software guy. I'm terrible at hardware, but I've always have aspirations to do more. So I thought, here I'm going to do a Steno keyboard. So the first problem I had is, of course, I wanted to produce the layout for my keyboard. So I used PostScript because it's Forth-like. It's fun. Every time I want to actually precisely measure something, I go to PostScript. It's fun. It has a Forth-like data stack. It's dynamically typed in fun ways. And it has a lot of the same virtues as Forth. It's very pithy. It's very, you can have, words for measurements and say, oh, here's a word that specifies an inch. So you can talk about 4 inches and this sort of thing, and box and all this sort of stuff. And this lets me describe, how I want to lay out a key in a definition, and then have a little domain-specific language to describe the layout of my keyboard. So there's a tiny little program that generates this. You can get the source code there up on my GitHub. Of course, then how was I going to do keys in the back of a sheet of paper? Well, I had this bright idea. So it's very easy to do capacitive touch, and so I discovered that tin foil is a fun thing. I discovered that it's very hard to solder between wire wrap and tin foil. I learned this the hard way. Again, said I'm not a hardware guy. I don't know. I don't. Aluminum foil, yeah. So in any event, yeah, I bet. So in any event, I discovered the hard way that did not work well. This is prototype number 1. Anyway, I did something similar on the back of these and ultimately just used tape. This works okay. I have far more problems with all the stray capacitance. Capacitance is a funny thing. And so anyways, there's this little device that I've actually got a kind of, I never got around to going to Jameco to get my 8x8 LED segment thing, so I'm afraid I have a 6x8 because that's what I happen to have sitting around, and a little counter. The counter actually was just sort of whatever I had sitting there, and it proved very handy because when debugging, you actually want to be able to see how many keys you have depressed to figure out what the heck is going on. And what I actually do, you can see this later at the kiosk, I have a little scrolling display on the display. Inside, I actually used some property of SVFIG, remarkably. A couple of years back at Maker Faire, we were handed an Arduino board. It's actually an Arduino Mega 80K. I was drawn to it because I had it sitting around, first of all, but secondly, because it has a lot of pins. It has enough pins for my 23 keys in my keyboard with some room for the LEDs and whatnot. And there's this lovely trick that I did not invent, which is there's a very simple technique to do capacitive touch where you just take a wire straight to the surface, and that's it. What you do is you put a little voltage on it, let it go, and then measure, and see how fast it takes to decay. If a finger is depressed, you've formed a little mini capacitor, and you can notice what's there. You have to sort of be very careful about turning off interrupts and all of this, but you can do this without any wiring. So all that's inside of this board, I'd open it up and it's a mess and disappointing, but essentially it's just I stuck a header on each of these sides and wire wrapped to the LEDs and wire wrapped to each of my buttons. So nothing but wire wrap, not a single component other than the Arduino board inside. My original intention was to turn it into a HID device, a keyboard. But unfortunately, the Arduino Mega is not actually capable of, at least easily capable of behaving like a keyboard. At some point, I'll probably swap this out for one of the other Arduino devices that is, and turn it into a real keyboard if I get ambitious, or if I decide I'm going to get an itch to do anything related to some physical object. But for now, what I did was I have actually found a different way to talk to it. And in particular, I've set it up to be a kiosk, which I'm going to briefly talk about. So I've got this hooked up to a Chromebook, which is not your normal computer. The idea with Chrome OS and Chromebooks is that it's nothing but the web. Well, it's kind of a lie. It's mostly just a web browser in a device. It has no native apps per se, but what it does have is, this is what the device looks like, Chromebook Pixel, this particular device. What it does have is something called a Chrome app. These are apps that you can install in your browser. They're a combination of JavaScript and HTML, and they have some additional APIs that they have access to. This is the key thing here. And the way the permission model works is if you've installed them through the Chrome Web Store or sideloaded them, there's some additional things that you can do. There's two types. There's extensions, which do stuff to the browser and let you do things like ad blockers. And then there's apps, and apps actually have sort of the richest set of device-related APIs, and there's two varieties of those. They have a variety of things. They can do local storage, proxy, and cabs, but the main thing is that they can do message passing. So you can talk between an app you have installed and a web page. And so a web page can effectively use an app as a device driver to reach out to the world and say, oh, I want to talk to this app. And then the apps have some specific API sockets and Windows and USB and Bluetooth, but they can talk serial. So they can talk to my Arduino board. And there's a bunch of other APIs. So you can query for the devices, you can connect to them, you can send things, you can do all this lovely stuff. And then you can set up message passing back and forth. And it's not hard. It's the actual amount of code to make that work is small. So anyways, how this is all ultimately set up is that you have the Steno keyboard. It talks to the browser / Chromebook over Chrome Serial, which lets it talk to the Arduino device, which is just printing and reading. This talks to the app, and the app uses message passing to talk to your page. And so the net result is that pages of my choosing can then reach out and touch and interact with the Steno keyboard. And so they can, it's two-way communication. They can receive keystrokes, but they can also send text to be displayed on the scrolling panel. And then you of course have to install the app in the store. This is further enhanced by something called kiosk mode in a Chromebook. The idea is these devices can be put into a mode where you can have it automatically log into a particular app and sort of lock it down. In fact, apparently they've started to grab the market for things like airport kiosks and whatnot. And the idea is that you can trust that the device is not being sort of tampered with. And there's a way to actually fully lock it down and say, basically, you have to completely re-image if you're going to get out of this mode. I have not done this. I've done a slightly reduced version of this. And after this is all done, I will actually switch it into kiosk mode and leave it over there for folks that want to fiddle with the Haiku site and fiddle with the Steno keyboard and see what it does. Thank you. Are there questions?
Maybe at lunch.
Okay.
Have one-on-one. Bob Armstrong.
And by the way, thank you.
Sorry to be giving these guys the hook, but as it is, we're going to be. If you really can't wait to have your lunch, it's going to be outside in about 15 minutes or so. We hope. So if you're really starving, make your way out to the back, but try to be courteous to the speaker. Otherwise, wait until it's over.
Well, by the way, try not to venture too far outside during the on day 8.
Now, this is the sort of database that I be able to live in, sitting in Bell here, be able to. Oh, I got to put on my.
Brad?
Oh. Oh, not that. There you go.
Yeah, okay. Am I live? Yeah, I will. Yeah. Gotta get here and clip it. Yeah. So this is, in a sense, the data structure that I want. I was gonna go and do this in PowerPoint, but I decided it was just simply easier to do it in Cozy. And one of the most fundamental keys in Cozy for day-to-day life is F11, which puts down a timestamp. And if you're dealing with lawyers, then put down an asterisk to turn on the time. Yeah, honored to be here with the creator of the language of today. I'm just working to come from Ken Iverson to bring, this is taking simplicity to the extreme, so I guess I'm taking two of the most simple minds that I've ever known. And point is to have a notation that is succinct enough. This is very APL-ish end of the spectrum, succinct enough to tweet great thoughts. And actually, I was in visual psychophysics actually at Northwestern and overlapping with Jeffy and so forth. But I never was interested in artificial intelligence. I wanted to artificially aid my intelligence and fit in a small head with a leaking memory working at my Peter principle limit, if people are familiar with that. Maximize my rate of making mistakes. And that ends up, really, it has to be something that remembers, and I can just execute anything I want, and you get down to it, fundamental level, it's going to be fourth. And everything, it's very simple structure. Everything is just text. We'll see in a few minutes, like this is just text. But I want a transparent structure all the way down to the chip. So whatever current or future architectures it's on, well, you know, yeah, it's open, it's forth. And uses, in a sense, from my perspective, Captain Picard's log. I want to be able to go and record what's going on and, you know, what the hell the judge said, but at the same time be able to do any intellectual sort of things that I want. And lots of different things that can be done within a sentence or two, in the notation. And really, and this is essentially just stating the essence of what I see APL, the thing about is starting with Ken Iverson generalized the notation from linear algebra. How many are familiar with APL, by the way? That's an astounding number of hands outside of an APL conference. Whoa, good. Okay, there is commonality here. Yeah, taking these two ends. And one of the things is, without question, you won't hear this, but Control S is the most solid part of the whole thing, because when you've gone and written down something, that is making this brain more solid than the leaky one up here. And you'll see everything is actually in a tree structure here, very much copied from Arthur Whitney, who's another very simple head, his K, which simplified APL to a large extent. And this is all unfortunately true, and actually this is my first touchscreen machine I got on my birthday on the 8th, and unfortunately it's already been court tested. But one of the things is, in some sense, more interesting and more valley is uses for the Internet of Things and any instrumentation requiring complex algorithms. So on whatever the hardware is, it's at my limit to get down to x86, but obviously, again, that's why. And I'm actually kind of particularly interested in 3D printing and visualizations and so forth, which are very, yeah, going and describing surfaces in sets of simplices is something I want to be able to deal with at the APL level. And actually, I see sort of in very fundamental level, the core challenge in getting from the chip to the APL is this transition on from a fixed address space to dynamic nested objects, and that implies, I'm following Arthur's structure on K here, reference counting. Instead of reproducing an object, going and keeping track of references. Here actually one of the, I'll get to what the different function keys are, but one of the keys that I've got sort of, if you will, special purposed, if should work out. Yeah, it's been, am I hitting the right key? Oh, I bet I'm not. Yeah, I don't know why this decides. Normally that should go to, oh, maybe it did. No, it didn't. In any case, it wanted to go and here, this is the structure of all the objects in COSY. And this I understand this is a bad link, but this was from Alan Perlis, if any of you remember some early people. But it's a single, this is the object header for all the COSY objects. First is type, where 0 means that it's a list of lists, that it's not a homogeneous list, because in the sense that integers and strings and floats and anything else you want to add as a homogeneous lists are you know, type. Count is APL row, how many items are in the list. Then actually this I've split. I'm not sure whether it's a great deal, because this goes and limits the number of references to an object to, well, in this case, 16 bits. And then this is the bits per item. And meta is something that I've transformed the way it is from what Arthur Whitney has. Meta will generally, either it'll be 0 with no object, or it'll be the address of a COSY object itself, which is generally a dictionary, which I'll show and so forth. Okay. Oh yeah, and dictionary is a list of 2 lists with names or symbols and associated values. And the root dictionary is named R, and there are vocabularies on lists. For instance, R, like I said, row is straight from APL, and that's it's a list of 2 lists, and each one of them, so it's a list of 2 equal length lists, 2 associated lists. And this is actually just a comment. I've sort of seen, and this is something that I think that APL gets a little clumsy at, actually. I sort of see in a lot of different situations, you end up having 3 related functions. And in COSY, these are at the raw 4th level. The index where, this gives you the address of the ith item in a list. But then there's a fetch and store on those. Same thing for whole lists of arbitrary lists at the reference, you know, the dynamic COSY level. And then for dictionary, it's in terms of a symbol or a name, and fetch and store, and then add and store. These, I said I was going to talk about this. Oh, actually, I like that. This is sort of a vocabulary of mine, because again, the purpose of all of this is to make things easier for my head. That's the purpose. I mean, I'm sort of so I'll use my cycles however I want to. But one of the things is actually, I don't know whether you can see it, but I kind of like this. This is one of those things to ease my head. Essentially, it's stack diagrams for all the different flips and flops and permutations and so forth. So I can just think of the stack diagram that I want to have it come out. I also mentioned that I would This is the stack frames that I followed, George, because there's so many recursive definitions that you're, you know, just everything's recursive. So these stack frames really allow you to go and have recursive locals and so forth. But I'll go on to that and get, because I want to just go, yeah, and a bunch of stubs of things that can be quickly done. To do, I got a to-do list. Oh, no, that's not the list I was thinking of. Anybody recognize what show that was from? I find sitcoms are the greatest soporific that I've ever met. Now this is executed directly, but I have you know, anybody who downloads and you know, finds this useful. Here's a bunch of things that need to be done. Martin Kromberg, actually, this is probably the best current you know, description of modern mainstream APL. Okay, and now, one of the things is that ends the time-stamped portion of the talk. I'll do a save and actually go up to, this is F1 is the key help. This is what you get when you download. There aren't that many keys that are defined, but most important is, like if I type stuff, let me just go and demonstrate this by mucking up my text. If I just type crap, I'm sorry, this is, so hope the FCC doesn't get on that. Then I hit return, okay, it just remembers, you know, it just, you know, it's in my notes. I hit Control S and it's for eternity. But if instead I type something that it can understand, let me just scroll down to one of these examples, as a matter of fact. Okay, for instance, R I said was the root. D names is essentially the first list there. So these are the names of all of the objects that are in the root, and that includes, for instance, the text itself that I'm in. Oh, by the way, I don't know whether people can see it, but here's the stack, whatever's on the stack here, number of useful buttons, let's say, and up here, whatever the last thing that I executed was, is listed up there, so you can see what things are. And just a couple more. Oh, I wanted to, let me, F1 again. Most fundamentally, what I just hit to go and do that, I just hit F6, bang. If I want to go and execute something in raw fourth, like 1, 2, minus dot, okay, hold down shift and hit F6 and that'll do it. So you can see that you truly are in raw help. And there are a bunch of, wrong, I didn't hit shift. Help, let's see, anything else to touch here? Okay, so, and F5 goes and puts down whatever the result was. Like if I just go and execute this again and hit F5, that'll put down the answer in my notes, which is frequently useful. See, this, oops, that didn't, oh, somehow got caps lock on. This screwed me up all summer because I don't know x86 and I didn't realize how absolutely essential that second, that inner thing is. Now, actually, the thing that's nice and pleasantly, CS help is the help on anything. There's, for instance, the contents, and actually there's a list of, well, this returns every occurrence in my source files of where that is. And actually that list of source files, our names is the same of the names. You'll see actually, browser, actually it's in sys. I think I can, yeah. Fetch. I can't see where the damn anymore. Yeah. Yeah, actually, that could it goes through all the dictionaries that are listed in here, and actually, in executing this little line, whoops, I hate that. Kind of stupid. If I actually there's stuff. Whoops. Let me get back here. There's stuff. Where's my stupid? Oh, okay. When it executes this line right here, going through all of those files, it takes those files, splits them on any totally empty lines. That's all the help information is right in the source, right with the source. And this just splits those files on all the totally empty lines and returns those lines which contain whatever the phrase is. And actually, in executing that line, it just created somewhere around 6,000 objects and then cleaned them all up afterwards. So that is, I think, the sources of I don't know why this thing, I mean, I've only had this for a week or so, but somehow, normally, I was doing it earlier, would go and start, Control F9 goes and starts the browser, whatever's browser. Those are the sources for the fourth, and for the graphical user interface here, which is IUP out of Brazil. Both of those, I think, are modules, which, not in the essence. These are the types. Everything's a list. There's strings, integers, floats, and, go for it. Right, the third part. Let me come. One of the things here when you download it, and this is much more, actually, I think to go and give you a nature of what Cozy looks like more normally, or in my working in the day, is here are my notes from today and going back next week and going back to, I looked up a guy who I'd met at this NOAA conference last summer, and he's with Picaro, which I wanted to get together with him. He unfortunately is over in England, but in any case, I had his name in my notes, so got to it. But in any case, you'll see that this is all my development up to going through obviously a lot, but I might as well. This is all what you get when you download the thing, for better or worse. This is actually when I got this and started setting up the sizes for the device. But one of the things, and this is a real essential thing here, is go and here. This went and just and it makes a cozy string. That's the 22 characters long, obviously. Now, if I take that and do that, take on it, bang, it reshaped it into a 7-row by 23 character long. This is a very APL-ish. I just showing, there it is, went and reversed it and stuck it back together. You can see the dupe there and attaching each. And then if I do that once more, looks the same there, but if I hit F5 to print it out, there we are. Any questions? So you can live your life. You can actually live a productive business life built and open to the fourth, right from, well, right now x86, but hey, you guys are the people who had computer science courses. So those were after my time. So Fortran? I had, well, the first computer I ever did anything on was an IBM 1620, which codenamed Cadet for can't add, doesn't even try. It did arithmetic by table lookup, but then then a PDP-8, that one thing earlier, but then I was on to what? Yeah, Focal. You remember Focal? Yeah. Yeah, remember going and rebooting all the, going through the, putting in the whole boot sequence. Yeah. Anyway, but then I learned APL, and I was really in visual psychophysics and wanted to be able to do the math. Now I want to be able to do the math, and this to me is one of the tremendous simplicities of Forth, is it gets away from the idea that a language is a horizon, as opposed to a dictionary, which actually, let me go to, this is my, in the beginning is the dictionary. and so that you gotta be able to get off the ground. And the thing is to go ASAP to the most powerful notation that you can create. So.
Well, with that, I'd like to thank Bob and all our speakers. I would like Dave and George for arranging for us to be fed. And speaking of the food, it's out back. Yay! Be very careful as you order something besides pizza to take what you order. All this part, please be very careful.
What? Oh, right. This got wrapped around, I think. I undid it. Right. Because I definitely have. It's really,
Wrong place. Other pocket.
No,
There we go. There we go. Thank you.
Good to see you.
Yes.